mic and key. As you heard, it'll be recorded and placed on the Mike and Key YouTube page. And well, feel free to talk amongst yourselves while we're getting going here. If you know each other, say hello or tell the people where you are.
My name is Doug, Alpha Bravo 7 Delta Golf. I'm down here in Tacoma. I'm active in the Tacoma Radio Club. I've been ham for 5 years now.
Okay. Very good. I took my tests, my licensing class tests at the Tacoma Club.
A lot of people.
Good evening, everyone.
They just want to listen.
We've got about 30 people so far. Believe it or not, I think we had over 100 people sign up, which means we'll probably have 50. Okay. And
He's the guy who's doing it.
Yeah. One,
Oh,
the one that's talking. Hi, Dan.
Hey. Hey, Bob.
Yeah, this
I'm
is
Dan.
Bob and Dan, and we're up in here in Mount Vernon, Washington.
I'm the current president of the Skagit County Club.
I think I'm seeing some clubs that I have presented at by Zoom before. Okay.
Yeah, I think, David, you did our club when I was president of the club, because I did a lot of people that were on Zoom, and your call looks familiar.
Okay. When you see me looking down like this, I'm looking at, I have a large monitor in front of me, and then I have my laptop screen to the right. Right. And so when you're doing this, I'm looking down at the laptop screen, because everything's much smaller, so I have to get closer to it. So just so you wonder, know what the heck is he doing? What's over there?
Hi, Chris.
Hello, Bob. What the heck is he doing?
And just to be in tradition for me and Zoom meetings, we'll start at 6:32, just to make sure the majority of people have come on board and we don't have as many, at least for me, as many people ringing the doorbell. Let's see, so far we've got Port Townsend and we've got Tacoma. Anyone else further out than that?
Cedar Woolley.
Okay.
Warm Beach.
Where's that?
Let's see here. In the Stanwood area.
Oh, okay. Got it.
Seabeck.
Okay.
Anacortes,
Seabeck.
and Stenwood.
All right. Getting good geographical pull.
I worked right around the corner from Seabeck for a little while.
We just hit 50, so that means that we're meeting what my expectations were so far.
John Greenfield, can you mute your mic, please?
My buddy Bill's there.
Bellingham.
All right, Bellingham.
Lake Bay, Washington.
Great.
Good evening. Good evening. My name is Mike K7. I am dealing with acid reflux and unable to speak at this time. I will be listening only.
Thank you for telling us that.
Yeah, thanks, Mike.
Orcus, okay. Okay, it's 6:30. We'll start in 2 minutes. Emmanuel from Kirkland. 55 attendees so far.
At $100 a person, that's a big mistake.
Yeah, I'm still waiting for that Zillow money to roll in.
Is that David?
Yes.
David Bob Triggs, W2IBK.
Bob.
Wanted to say thank you for sharing all this.
Oh, my pleasure. Hopefully you'll all get something out of it.
This is Shelley, KE0TUG from Sarek.
Great.
Hi, John.
Say, David,
Yes.
this is Musa. This KI7ZOO. I lost video. I don't know if you can see me good. The first
Oh,
time,
I see your video.
the first time on Zoom, so I'm trying to figure that one out.
Okay, great.
So I'm good. Huh? Okay. Thank you.
Okay, 61. Okay. All right. I would love it if everyone would put their mics on mute. And then there's no background noise. When I go to Q&A period, then feel free to turn your mics on. Thank you. And it's 6:32. We've got 65 people on board, so we can get going. I think we got a quorum. So welcome. Good evening to everybody to Getting Started in HF Operations. It's a primer to help you start surfing the ionosphere. I'm David Okrent, your presenter today, Whiskey 7 Delta Alpha Oscar. I'm an extra class licensed amateur radio operator, a VE, and an instructor. And hopefully I'll be able to give you a good overview to get you started if you haven't done much HF. And if you are a veteran HF, maybe we'll find something interesting and new that you didn't have before. So again, welcome, and I thank you very much. And I wish I could donate to you guys a t-shirt that says I survived a 3-hour Zoom meeting, but it is unable to do that. So a few things to go over. One is, this is a primer. As I said, it's an overview of a very wide and deep subject. And when I'm teaching this, especially in a general course, some of these subjects all together that we're going through could be 5 or 6 hours. So I go in a little bit deeper. Some of you may have heard me speak about one chapter of this at one of your club meetings, which usually is about an hour. So kind of figuring out how to pare it down when I'm the kind of person who likes to put lots of things in. So we'll see we'll see if I made the right balance. But again, so therefore I just want to make sure it's not a comprehensive course. There's things I have to leave out, and there are things that you may know that you say, why didn't he put it in? It's because I had to decide how to do the timing. And the goal of course, the presentation is to convey enough information for you to take your HF privileges and get on the air. I will say that I do have some images of products that are used in this presentation, and these are not endorsements. I'm not getting paid, so these are not advertisements. They just happen to be convenient for me to pick up. A couple of items before we get into the lecture itself. During the presentation, I will not be able to see the chat or participant pane. Therefore, don't ask me questions via chat or raise your hand, because most likely I will not be looking at that monitor most of the time. And it's also very small, so I have to go all the way down here to see it. And so therefore, wait until I have a chance to break for questions and then go ahead and speak up. Of course, feel free to use the chat amongst yourselves during the presentation. Unless this distracts you, and then please close the pane if it's distracting for you. But feel free to chat amongst yourselves if you'd like on the chat pane. I will stop, as I said, periodically to answer questions. I suggest you write down your question and hold it until this period. Now, in some situations, I will ask people to share their experiences or stories around something. Because of the density of the material and the rate that I'm going to be going through, I'm going to ask you not to share your experience and stories during the Q&A period, but feel free to put those in the chat pane again, but not use them in the question period. There'll be a few 10-minute breaks so that we can, stretch, do some bio stuff. And occasionally I will not be breaking, and I'll tell you when I'm not breaking, and then you can actually ask me questions during the break as well. And of course, afterwards, if you have questions after the presentation and you want to or share any feedback with me about how things went for you, please feel free to email me at w7dao@arl.net. So I'm assuming everyone can hear me fine. If anyone can't hear me very well, can you please just indicate that by going off mute and telling me? Okay. Okay, so here's our agenda, because like any good corporate person, I always have an agenda. We're going to cover 9 chapters at various depths. Of course, I'm going to share the fun of operating on HF bands, some things about the ionosphere, antenna basics, the key thing about maximizing power transfer, some basic transceiver functions, some operating etiquette and things, and how to power it all up, and briefly on going digital. So I will also put my phone up so I can see the time, so I don't screw up my timing, which happens. So with that said, again, I want to thank you all for coming to the class, and we'll go ahead and start digging in. We have 69 people. That's great. Okay, so let's talk about the fun of operating on HF. At least for me, the fun of operating on HF. And I like to think about HF as piloting a sailboat that's under constantly changing weather conditions, but without the queasy stomach, because I suffer from severe motion sickness. That's important for me. So that's what I think operating HF is like. And what makes it fun is, long distance communications without a need for a space station, bouncing off the moon or a repeater, the ability to meet new people. And I've had some conversations with people from all over the world, not just having a quick exchange, but actually learning a little bit about them and what they do. And because the ionosphere is always changing, every day is different. What worked well yesterday doesn't necessarily work well today. Also, I'm kind of like to tinker, and so I'm always playing with new antennas or new ideas for how to get my signal out there. And recently, I started doing a lot more QRP operation, which has been opening up that for me and seeing how low could I go and still make a contact. So those are just different fun things that you can do, and everyone will find their niche and things that they find that are good for them. What you're seeing on the other side, the picture of me, that is me without my mustache. And I'm operating in the field. And that's my FT897D, my previous radio with an LDG tuner bolted to the side of it. which is how the FT897D deals with a tuner. And I think this was a field day picture, actually. And so what's interesting for me when I operate HF is, for me, it's really about how far can my 20 or 100 watt light bulb be seen? And that's kind of what I find is challenging. That's what makes it fun for me, is to think about how low that power really is, what the equivalency is, let's say, in a light bulb, and the fact that that small amount of energy is being picked up by somebody from a far off place. That's kind of interesting. It's fun, and it just is still, even though I know all the technology around, it's still awesome and awe-inspiring. And the thing about HF is we often think about it as towers and big antennas and lots of power, but it can be as simple or as complex as you want. And here's some of the ways I operate. This is with a G90 20 watt QRP radio. And you can see on the far, my left of my screen that's my car with a 16-foot antenna at the top. And then you see there's a ham stick on the right, which is a ground-based vertical with radials. And I've been able to cover as far as 5,400 miles on 10 meters with that 20 watt radio from that setup. So it doesn't mean that you always have to have a huge setup, complex setup to get things done. You can just get things done as well as you can, as simply as you can. But of course, your expectations would change, because at 20 watts, I'm not going to necessarily break every pileup, versus if I had 400 watts, I probably would be breaking every pileup. So just keeping that in perspective. But with the solar cycle, 25 being much more active than 24, that 20 watts does a fairly good job these days. And my longest contact for my career as a ham radio operator with 100 watts has been 8,300 miles from Seattle to Tasmania. And when I put this together, it was kind of funny, because I don't usually go for awards, and I don't usually, do a lot of thinking about all the different, I'm not really good with logging things because I'm lousy with processes. So, but then I started picking it up and saying, well, gee, I've pretty much got almost all the 50 states. So I've got to work on that now and go document that for a Worked All States Award. And then some of the countries I've worked is, as you can see on the left, Ireland, Canada, Spain, Argentina, Cuba, Slovenia, Solomon Islands. And one of the things to think about is there's two things going on here. One is you're transmitting, and the other is that person's receiving. And so you might be operating 20 watts, but if that person, like in Slovenia, has a superstation with a large antenna, beam antenna, elevated really high, that's great for you. That's going to make your contact go a lot easier with them than if you're just trying to pick up somebody from another, QRP small vertical antenna. So the other station has a factor in whether you're going to talk to them in QRP or even at long distance for 100 watts. Is what the other station is doing does have a factor. But this is the kind of fun thing for me. How far can that 20 or 100 watt light bulb go? The other thing to think about is where the allocations are. And to get the most fun, if some of you on this phone are technicians, if you want to do HF and have the most fun, you need to upgrade. And upgrading to general is not difficult. In fact, sometimes I've taught a tech general combined class so that people can test out with both licenses in the same test session. It's not a big leap from tech to general. It is a much bigger leap from general to extra, but it just means how much time you want to spend studying and getting prepared. But I do recommend, if you like HF, if you're interested in HF, it's really nice to go ahead and get upgraded. It's not difficult. It's just time and energy, as we always say. The thing I want to point out on the right on the screen is, in the bold at the bottom, is the SSB, the voice area of 10 meters at 28.3 to 28.5 megahertz. And that would look like, well, that's kind of narrow. But the answer is that's really, really busy for international communications when you have a good solar cycle situation like we're having right now. So it's not unusual to have European stations, South American stations, and Asian stations in that space, and with very little wattage and a decent antenna getting through to them. And so even if you're a technician, if you have access to a 10-meter transceiver or something that has a 10-meter band in it, you can operate it and operate voice. So if you have that ability and you're a technician, give it a shot and see how that goes. And I bet you'll catch the bug and upgrade, because if you see on the left, There's a lot of space that you have as a general or an extra up there, and that you can take advantage of. So before we go into the bands, I'll just say this was a really quick introduction. Anyone have any questions about what we've just covered? Feel free to come off mute. Okay. Great. So let's dig in a little bit more on the bands. Go ahead. Someone have a question? I'm sorry.
Yes. You said, what was the expression? Break a pile up.
Ah, the minute I said it, I realized I didn't define it. So you want me to define that, I assume. I jumped ahead of your question.
Please.
So let's assume that you're in a stadium and you're one of 10,000 people in the stadium, and you all want to send a message to the umpire behind home plate. And guess what? You all yell out that person's name at the same time. So that is a pileup. Everyone's trying to contact the umpire or the station that they're interested in all at the same time. And it's a cacophony of different stations. And so if you can think of everyone yelling at the umpire, I want to speak to you, with their name, saying David, John, Julie, Deborah, they're all yelling out their names at the same time, and hearing the umpire saying, okay, Julie, come back. And everybody goes quiet, and then Julie speaks. That's working a pileup. Does that help?
Yes, thank you.
Okay. And it can sometimes feel like that. So a little bit overview of RF bands. HF, as we said before, is in the 1.8 megahertz to 30 megahertz range. That's the high frequency band. And just to remind you that what these mean is we have VLF, very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, and my favorite, exceedingly high frequency. And so, believe it or not, we have, not believe it or not, you're all licensed, so you know that amateur radio, we have islands of allocations across this entire span. But we're really, when you think about, we're kind of sitting, if you want to put it in colloquial, in common terms, we're kind of sitting between the AM band and the FM band with the HF. And so we have some characteristics of medium wave propagation and some characteristics of VHF propagation, depending on where you are in that red zone. Also, amateur allocations, one of the things, they're not uniform from country to country. So different regions, different AIRU regions may have slightly different allocations in spectrum than the North American areas. So for example, as you can see, Europe, Africa, Middle East, and Northern Asia don't have the same amount of bandwidth in the 40-meter band as we do. They go up to 7.2 megahertz, and we go out to 7.3 megahertz. And Japan as well doesn't go out beyond 7.2 megahertz. And the color coding you see here is the different types of emissions or modes. So these are, so your CW, RIDI is radio teletype, which we'll talk about towards the end. Phone is voice, and you can have AM voice, FM voice, or SSB, single sideband voice. And SSTV down there stands for slow scan TV. Think of it as one picture slowly developing on your computer screen at a time versus full motion TV that you're used to seeing on broadcast. By the way, in the UHF area, there are people who do amateur TV, which is at full frame rates, and it has full motion capture. So one of the things to think about is if region 1 stops at 7.2 and region 2 stops at 7.3, how can region 1 communicate with region 2 when they want to talk to a station that's above 7.2 megahertz? And we'll get into this a little more, but this is a very not an unusual situation, and it's called operating split. So here's what, and if you're used to repeaters, it's kind of like the same kind of thing that we do with repeaters, but it's done in HF. And in this case, let's say the station transmitting from Europe is at wants to talk, it's usually the other way around. Let's say I'm in region 2, I'm in the Americas. I want to talk to a station in Europe, but it's the best situation for me is in the 7.25 megahertz range. Now, the person in Europe might be listening across the entire American band, but they can't transmit there. So they hit me at 7.25 saying CQDX. Is anyone out there long distance? And I might say down 20 or down 1 or down 10 or down 15. And what that tells person is I'm going to transmit at 7.25 because that's in my allocation. This is kind of not, now that I think about this question, it doesn't really work well. I'll have to explain it in a different way later, but I'll give you the essence of it because it doesn't really work now that I think about it. So they're listening to me at 7.25, and I've notified them that I will they can transmit in their band, and I'll be listening at a different frequency. So it's sort of like a repeater. I'll be listening at one frequency and transmitting at another. I tell them that so that they can now communicate to me out of their band allocation. This was not now that I look at it, it's not a great example. We'll get into a better example of split a little bit later on, but just understand there's something called split, which allows me to operate my transmission and my reception on two different frequencies on HF, not like a repeater, but the same concept of a pair of frequencies. I'll come back to that. I realize now as I talk about it, it was not a good example in this case. So thing about a band plan is refers to, and this is important, a voluntary division of a band to avoid interference between incompatible modes. So most band plans are not legislated. They're not something where the FCC or the Australian Communications Commission or the equivalent in Britain, they don't legislate the band plan. They allow the voluntary organizations in those countries for amateur radio to then develop those band plans. And so that's to keep that in mind, so that someone says, wait a second, you can't operate that mode in that location. The answer is we don't recommend it, but you could because it's a voluntary band plan. But not everybody remembers it's voluntary. So here is the US amateur band plan. What I did is I grayed out everything but the HF section. And 160 is really medium frequency, so it's not technically in the HF section, but oftentimes it's lumped in there. You might, by the way, hear it referred to as the top band. It doesn't, from a frequency point of view, it's actually the lowest band, but it's often called the top band. Maybe it's because of the number of meters the signal goes out. And so here's our allocations. Again, we talked about them earlier. It's interesting to note, if you see some of the key stuff on the right side, CW operation is permitted throughout all the amateur bands, which means you can operate it anywhere. It doesn't mean, again, band plans are only are guidelines. Now, again, if you operate against the band plan, amateur operators might say to you, hey, we don't do that. So, but it's just understand that it is voluntary. And so this is I have one of these almost, a lot of people operate HF have one of these in their station, have this put up. Some of them just, they've operated for so long, they know it off the top of their heads. And one of the things that I recommend is if you can program frequencies into your radio, which generally in modern radios you can, then for me, what I do is for each band, I program one memory for the start and one memory of the end of the typical area I operate. So for example, if you're a general licensee, general class license holder, if you want to operate the 40-meter band, you might set a memory. If you look at the 40-meter section of the band plan here, you might set a memory for 7.175 megahertz and the other memory for 7.3 megahertz. And that way, when you push the memory key, you're going right to the beginning of your general allocation. And you also have a memory key at the top of your general allocation, because sometimes you want to scan down and sometimes you want to scan up. But this way you don't have to go back to the chart and make sure, am I in my allocation? You've programmed it into your radio so that you just push the button and say, okay, that's in my allocation. I'll kind of tell you a little, I took one look at this chart as when I was studying for my technician in general, took one look at the chart and said, this is too much for me to keep track of. I'll just go extra and then I'll just not have to worry about where my allocation is. It's in the right place. So that was probably one of my biggest reasons for going to extra right off the bat, was because I didn't want to have to remember where my allocations were. Then when you're operating, one of the things that you can do in a lot of radios, when you pull up the memory, let's say 7.175 megahertz out of memory, you're able to tune from there with your HF radio. It's not channelized, so you can just go into what's called memory tuning, and it'll just tune from wherever the memory channel started from. And then you can add into your memories of your radio the QRP calling frequency if you want to, if you do QRP operation. There are other types of calling frequencies you can put in. HF nets, just like there are 2-meter and 70-centimeter nets, there are HF nets on different frequencies, mostly on 40, 20, and 80, if I remember correctly. Also, one of the things that I do is I program all the National Bureau of Standards WWV frequencies, which I'll show later in the presentation, into my memories. And I do that because when I sit down to operate, I quickly scan the WWV frequencies to hear the quality of the signal coming from Denver. And from that, I can tell which bands are open at my location, which bands have the highest probability of me making a contact, because the louder I hear on that band, the better that band is to be open to make contacts on. So I use it as kind of what's called a beacon to help me figure out what's happening with the quality on that band. Because unlike 2 meters to 70 centimeters or 220 megahertz, where it's FM, it's often repeaters, where the quality is essentially always the same. In HF, as I've said earlier, it's like, basically sailing on a chaotic sea. So every band, every day, even out over a period of hours, is changing how well it's propagating. And then to get a little bit more confusing, the band plans are more complex. So if you remember, this is a very simplistic view of the band plan. There's some color coding. But if you really want to understand the band plan, there are other places on the ARL site and other places where it gives you a bigger breakdown where the CW, you can see in the green area, where the CW calling frequency is, where the ARL is going to be sending their code practice stuff. There's different nets that are located there, where the 14.230 is the SSTV frequency. If you want to listen to or decode slow scan TV, you can go there and you'll hear it from periodically if someone's transmitting. There's an AM calling frequency for those who want to try out doing amplitude modulation. And of course, each digital mode has their own calling frequency that they are on. And that is by, basically convention of everybody saying, yeah, that's a good spot to put it. Let's go there. And just over time, that becomes the frequency where people look. Does that mean that you have to be there? No. But if you want to contact the other people being digital, there's a high probability you better stay there and to make those contacts. I'll stop here really quickly and just see if there's any questions for me.
This is Musa.
Yes.
Got a question on the split. You said we can receive on one and transmit on another one. That specifically some radios might have it, or all radios will have it?
We'll get into it. Pretty much most radios do have split operation.
Oh,
and
okay.
I'll do a better explanation of why split is worthwhile. But I will tell you that I've probably operated over the last 10 years, split twice. So it's oftentimes it's not really common, but it's not unusual. So, but almost every radio I've seen has split capabilities.
All right, thank you.
Okay, other questions before I go on?
Yeah, Elizabeth here. What is WWV?
That's the National Bureau of Standards atomic clock chimes being broadcast on the radio at different frequencies. So you'll hear, a tone, dong, 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 dong every second. And then at the top of the hour, you'll hear at the tone, it will be, 23 hours, 36 minutes, coordinated universal time, beep, ding, 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 ding. And that's, there's a good reason for that being there, but it's also on different frequencies in the HF band. So you can listen to that for the quality of how well you're picking it up to make a deduction about how well the band is in that location. And it's, by the way, the other reason it's broadcast, it's used for astronomical observations as well. Is that okay? Did that answer the question?
Yes, thank you.
Okay. Any other questions before we go on? Okay. So what to be expected, but not always for each band? Well, that's a really interesting question. So basically when you're down into the 40 meter, 30 meter and lower frequencies, that's 30, 40, 60, 80, 160, you're really looking at a nighttime band, primarily for any distance. If during the day, it'll be much closer in communications, which we'll talk about as a space wave versus a sky wave. And so at 160 meters in the 1.8 megahertz to 2 megahertz band, the ground wave is going to dominate, ranges about 50 miles. So that's right above the AM bands. So think about that's very much like what AM radio is like as well. But remember at night, if you remember oftentimes listening, usually a lot of us listen when we were kids, the AM band at night, and you heard distant stations, it's because the ionosphere D layer has disappeared. What happens during the day is the D layer appears and it absorbs a lot of the lower frequencies of the HF band, and that's why it can't travel so far. But once that disappears, it opens it up. So 80 meters you can see from 300 miles, and at night to 1,000 miles, and then it goes up from there. At 20 meters, we kind of have a changeover, and it is better, technically, it's better during the day, but it closes down at night. So anything up from 20 meters and above kind of acts that way. It is going to be open for long distance during the day, and it's going to close down a lot during the night, except at higher sunspot levels. So typically, it's not usual to get 1,500 to 3,000 mile contacts or even higher on the 20 meter band during daytime. And if the solar cycle is good, that is the same for everything up to 10 meters. So, but again, it typically tends to close down at night for long distance communication. So it's kind of that transition point is at 20 meters. But the important thing is these are rules in general. It doesn't mean this is what's going to really happen. As they say, your mileage may vary because remember, it has a lot to do with space, weather, and our atmosphere and ionosphere. So right now, this is as of today. Look at what's down there. During the day, 8340 meters on the lower left is poor conditions. At night, it's fair. 30 to 20 meters, fair to good day through night. And you can see, wait a second, David just said that 15 meters would be shutting down most of the time at night. Nope, not today, because of the way the ionosphere is and and what's going on up there. The propagation is going to be different. The band's going to be a little bit different in its activity. So we'll get into some of these numbers that we have here today on later in the presentation, but understand that ham radio operators are kind of a strange group. We're the only people in the world who, well, we're not the only people in the world, there are other people, but what's strange about us over the average person is most of us are listening to two weather reports. We listen to terrestrial weather and solar weather. And so, and there are times during the year when if you look at 6 meter, it says ESEU up there. Sporadic E, which I think we'll talk a little bit about, but sporadic E, which affects 6 meters, is like all of a sudden a piece of the ionosphere, and it's just a piece, lights up as far as it gets very energetic, becomes much more reflective, and now 6 meters, which would have blown through the atmosphere into space, now bounces off the ionosphere and can be now used for skip. And there are people who that's their thing is 6 meter sporadic E. That is their thing. They have places on the net when someone calls surfs up and they basically grab their surfboard, so to speak, and get on 6 meters to try to make long distance contacts. So it's everybody has their thing that they find the most fun. It's one thing about amateur radio, as you guys know, is that there's something for everybody in this hobby. And what you start off with when you start the hobby may not be the thing you actually gravitate towards over time, or it changes and there's always something new to learn. So as you can see, there's things that you probably recognize from your other ham classes. MUF, maximum usable frequency, is listed here. And this is located at Denver, by the way. Signal noise levels in that location are S2, S3. I live in Seattle. My signal to noise rate level is more like S7 to S9. And so it can get, like I said, your driving mileage may vary. So that's a good introduction to the ionosphere. So let's talk about the ionosphere a little bit. I know we're going fairly fast. So if I'm going too fast, feel free to come off and say slow down on something. because sometimes I'm not aware how fast I'm talking when I'm in a Zoom condition. I don't have as much feedback from the audience. So feel free to come off and say, can you slow down a little bit? And I'll be happy to do that. So let's surf the ionosphere a little bit. So first, let's start with that big, really big fusion furnace up in the sky. So as you know, it's a massively radiant heater. It's the source of high energy particles and other stuff. And specific wavelengths of UV and X-rays are what's energizing monoatomic and molecular oxygen and molecular nitrogen. And they can lose an electron or electrons to become ionized. And once they've become ionized, they can now reflect certain radio frequencies. Now, one thing to consider is that when you've ionized an atom, when that atom has lost electron, it wants to get that electron back. So it'll do whatever it can to become neutral again. So wait a second, if it wants to become neutral again, how do you actually have an ionosphere where there's a lot of kind of free-flowing electrons and atoms that are missing electrons? Well, it's because there's enough energy hitting the ionosphere that the rate of recombining with the electrons is much lower than the rate of the electrons being excited and leaving the atom. And that's why you have an ionosphere, is that rate between losing electron and getting electron are out of balance. And so when it's really, really energized, you're going to have more electrons that are free-flowing and less atoms are able to become neutralized again. And so that rate difference is what's creating that ionization layer to be stable, relatively stable. So of course, you're going to find out in a second why it changes for the same reason. So the RF signals experience ionization in different ways. They can be reflected, they can be refracted, they can be absorbed, or a little bit of everything. And mostly it's a little bit of everything. So when you go through the ionosphere, not all of the energy is reflected back. Some of it's going to be absorbed. Some of it's going to be refracted. So even though the D layer and the E layer and the F layer can reflect to some degrees, there is some absorption that always goes on. So one of the things that when I first did my lecture on the ionosphere, and I was developing it years ago, I realized as I was walking through Costco that the Earth is like a rotisserie chicken. And if you think of the Earth it's kind of a rotisserie chicken. This is not a really good picture of that rotisserie, because if you think of those big industrial rotisseries, the chicken's not only spinning like this, it's spinning around the heat source. It's revolving around the heat source as well. So you have to put that together. And because of that revolution that's going on, the spinning of the Earth and its seasonal rotation around the sun, our Earth chicken has temperature gradients. So if you think about it, the top of the planet Earth in this picture on the right is going to be cooler than the bottom of the Earth in that picture, because the radiant heat source is closer to the Earth on the bottom than it is on the top. Well, that sets up a temperature gradient across the entire Earth. And this is what's happening, is that we don't have a uniform temperature, or I should say a uniform excitation of the ionosphere across the Earth, because there's no sharp boundary. It's all a gradient. And so in this gradient, we have lots of changes in the energy level. So let's go back to the sun idea with ionization. Remember I said that the reason we have ionospheric layers is because there's enough energy that ionizes the atoms, but they can't recombine to become neutral to neutralize the effects totally. So if you have 100 atoms that got ionized with that much energy, they can only, let's say 50 of them can recombine, which means you still have an ionosphere, those last 50 that are still ionized, and they still can reflect radio waves. But when we're on the night side of the planet, we don't have the sun heating it up directly. So now we have a higher rate of recombination between the atoms and the electrons that become more neutralized. So instead of having, let's say 50-50, as I described in my previous example, they could now be 20-80 or 30-70. So the ionosphere will then change its characteristics, and it changes those characteristics over a gradient. So it's not a sharp, it's now night, it's now day. It's not night, it's not. That's a gradient. The temperature is changing over a period of distance and time. So this is important because we are going to hear sometimes in HF about this idea of a gray line. And the gray line is that transition of temperatures between the night side and the day side that allows us to have some very special propagation characteristics we'll talk about in a minute. But during the day, thank you, about the rotisserie chicken and shopping at Costco. During the day, as a lot of you learned in your classes, there's enough energy and the density that occurs between different molecules with different energies penetrating the atmosphere. You get an F1 and F2 layer, you get an E region and a D region. And then on the other side, when things are nighttime, the energy levels have dropped, so the F layers are then combined back together. They're a bit smaller. The E region is by itself, and the D region there's not enough energy to keep the D region going, and it just disappears. And because the D region is gone, that lower part of the HF band now can penetrate to the E and F regions to do skip. Until that point, the D layer was absorbing the energy from the lower parts of the HF band. Okay, one more, and I'll go through some questions here. So this is a little bit more interesting about how it works, but basically it's telling you the penetration in the atmosphere of some of the energy coming from the sun. The X-rays are what are basically energizing the D layer, and then you have different levels of ultraviolet that are energizing different layers of the atmosphere for ionizing oxygen, nitrogen oxides, etc. And you can see the altitude on the left, and then a little bit more about what's happening in the graphic on the right. So, but the thing is, you can see that there's a troposphere, stratosphere, mesosphere, thermosphere, and then we have a special, and then we have the ionosphere. So one of the things that can be confusing is that the ionosphere is kind of crosses those boundaries of the mesosphere and thermosphere. And so if you look at a diagram saying, well, hold it, I don't see the ionosphere there, it's because it is happening across both the mesosphere and the thermosphere. So, and then one last thing about just here, and I'll stop for questions before we finish up. And let's go back to reflection and refraction. If you look at the diagram on the right, you'll see as the RF signal's coming in from the top, that's the angle of incidence, the signal can be reflected. If the type of layer you're hitting will reflect the frequency, it'll reflect. It can also go through that layer and be slightly bent, like a lens bends light or a prism bends light. That can be refraction. And so as it goes through that layer, it could be bent, or it can be absorbed, or it can be some energy of all. Some will pass through, some will get absorbed, some will get passed through and become refracted, some will get reflected. And so you can have both things happening at the same time. I'll stop here. Any question before we go on about these items?
Yeah, I have a question about the slide about the solar weather. You mentioned about the noise level, that it was S2, S3, and you mentioned that being in Seattle, it was like S7, S9. I can probably look up more details somewhere else, and this is just a summary. But can you please give a very basic detail what this means, what the noise level is,
yes,
and why there is a difference by geography, and how can you find out what your local noise level should be, and what is the impact of these changes?
Okay, so let me break it down to two pieces. There are two basic sources of noise. Atmospheric, natural, and that's a major source of RF noise. And so where this radiosone, which is what the device they use, a radiosone, picked up, is that the noise level was fairly low. There wasn't a lot of natural atmospheric noise at that location when they did it. However, there's a large component in cities, especially, of man-made RF noise. That could be bad power line couplings. It could be LED lights that are not designed properly. It could be wall warts. It can be your computer power supplies. There are many, many different levels of types of RF noise generated by man-made objects. And so I live in the middle of Seattle, so I'm now hitting every possible man-made source of RF in my house and around my house is coming into my antenna. And that is giving me a higher noise level. So I have the atmospheric noise plus the noise. And so if I were to drive out to Cedro-Willie, someone said Cedro-Willie, the noise level in Cedro-Willie, because there's less man-made sources of noise in Cedro-Willie, will be a quieter for me to do it, to operate from. So that means that to get the best contacts, I have to hear them. And if I have such a high noise level, I can't hear as many people as someone with a lower noise level. Now, I'll talk to you about how to get around that a little bit later, but the bottom line is those noise sources that produce the most noise are man-made. Now, it's possible that you have solar weather situations that energize the ionosphere so much that the noise levels become basically, high, or worst case, I should say, the ionization level is so high that there's a radio blackout. You can't hear any sky wave. There's no reflection because it's all absorbed. So very simply, there's natural atmospheric noise like thunderstorms, usually relatively low levels of noise for us, and then man-made noise, which is oftentimes close proximity to us, much higher. Does that answer your question?
Sorry. Yeah. Yeah.
Okay.
Perfect. Thank you so much. That was very useful. Thank you.
Well, okay, I should not use Cedro-Willie then. I was hoping you were in a better situation. Okay. Other question before I go on? So different. I've never taught this kind of class for this length of time without being in person. So it's a new thing for me. So again, we're thinking about reflection, refraction, absorption. So the sky, the way I look at it is the sky is full of millions and billions of RF mirrors. Every ionized atom and molecule is a mirror for RF, or a refractor to RF, or absorber. But in this case, we're talking about it as a mirror. So think about it as we have billions and billions of mirrors in the ionosphere, and the net vector of their direction, so to speak, is how we traditionally think of that layer of the ionosphere. So when we say it goes up to the F layer, it bounces down in this kind of pattern, it's because we have generalized that the net vector of all these mirrors' aim is to go downward. They don't always have to go downward, but we generalize it to be downward. So you can then have different types of skip, because as you notice, you're hitting the ionosphere. Remember, it's like a chaotic river of ionized molecules. You can hit one section of the ionosphere where you're just going to go up and down pretty straight, and other levels of the ionosphere where you can go up and it's canted a little bit and you're going to have a different propagation. Now, the difference in here is you see that the way the blue line and the orange line leave the point on the left, that's called the takeoff angle. And all antennas have a takeoff angle. That takeoff angle could be 5 degrees, 15 degrees, 20 degrees, could be 90 degrees. There's always a major lobe of energy that's called the takeoff angle. And if the takeoff angle is in a low angle, then you have a longer distance to get up to a reflecting ionization layer, and you'll have longer skip. If your takeoff angle is much closer to 90 degrees, you're going to go up and be reflected to a smaller distance down, because the angle of incidence is equal to the angle of refractance. And then, of course, you can always have some strange things happen, because where you hit the ionosphere, it could be tilted relative to the ground, so to speak. And that's a really not a great term, but it's the best way I could describe it. Relative to the ground, it could be tilted in such a way to give you a better angle as well. So just think of this as a river of billions of RF mirrors. Essentially, they're all kind of have an average of where they're pointing, but on the micro level, when the radio wave hits it, it all depends on what angle, so to speak, that quote river or that mirror is. And I'm using the term very loosely. I'm just using it as illustration, not as a actual description of those ionized materials. So here you have an example of we have the blue RF coming up, going, and in this case, it is now refracted through the ionosphere. So it's going through that layer and it's being bent. And now it's hitting an upper layer and it's being now bounced back down to the earth. So if you think about it, if that blue line hit the blue part of the purple part of the ionosphere and was reflected at that point, it would not go as far. But because it got refracted and moved up to another layer, it can go further. Now, will there be energy loss in that product? Of course, there'll be some more. It's longer distance, there's more energy lost and absorbed. But that's one of the ways you can have a complicated skip pattern. So sometimes it's really difficult to figure out what the heck's going on up there, but you can have these kind of things happen all the time. Okay, and then you can have, because again, I've said, you can have these things hit the ionosphere and point it, and the way things are energized can point in various ways. You can have literally something like this, where it hits the ionosphere and it's reflected horizontally, hits another section of the ionosphere, and then then bounced down to the Earth. So that you can have that kind of ducting across the ionosphere that can occur. So it is really strange stuff. It's the spooky stuff of RF. So a lot of you are familiar with this. There are three basic waveforms that we deal with from an antenna in HF: ground wave, space wave, and sky wave. The ground wave stays stays relatively close to the ground. This is that tricky question that happens on some of the amateur radio tests, which says the visual horizon versus the radio horizon. The radio horizon is slightly longer than the visual horizon because of with respect to the ground wave. The space wave is that communication that's going through the air, but it's not going up to the ionosphere. And that would be like VHF line of sight, would be like a space wave. And you can have line of sight communication in HF as well. And then you have the DX, or the long distance sky wave, which is going up to the ionosphere, passing through or part of the ionosphere, and then coming back down. And what's interesting here is when a sky wave is coming down, goes through the ionosphere, as it exits it through all the different layers of the ionosphere, excuse me, it becomes elliptically polarized. So when you think about it, in space waves and ground waves, we ideally like to have the antennas have the same polarization. So if you think about 2-meter FM, we want to have everything by convention vertically polarized. Why? Because it's basically space wave. So whatever polarization it's leaving the antenna is the polarization it's hitting the receiving antenna. So we'd like them to maximize energy transfer. We want to have them at the same polarization. If we're doing SSB in the 2-meter band, by definition, that's horizontally polarized. It's still space wave. So the receiving antennas should also be horizontally polarized. But in HF, you'll notice we talk about horizontal. We don't really talk about, we don't make a big emphasis on vertical versus horizontal orientation between the transmitter and the receiver, because essentially the skywave's coming down elliptically polarized. And so it doesn't matter which way your antenna is oriented. It's going to all be, it's not going to be optimized because when it's elliptical. Elliptical is just a slightly non-circular way. It's a non-circular version of circular polarization. And remember, you can have left-hand and right-hand polarization for satellite communications. But when it goes through the ionosphere, just remember it's elliptically polarized. That's the reason why people don't harp so much on making sure the transmitter and the receiving antennas in HF have the same polarization. And of course, this is not an unusual picture. I'm sure you've seen some version of this in your technician class. You can have, like I said, all sorts of different ways that things are bouncing through, how many different bounces it takes. You can see the chordal mode, which I demonstrated with my illustration earlier. You have the ducting mode where it's bouncing between layers until it finally comes down. You have that highly energized localized area called sporadic E, which then causes it becomes the ability to do more bouncing, more skip. And so you can have 1 hop, 2 hops, even 3 hops, depending on how much energy is still there for the other station to pick up. So oftentimes we say in the Washington state area that Alaska and Japan are 1 hop. But getting to the East Coast and even to Europe is a lot more hops, a lot more difficult. But we can, people go, yeah, you got Japan. People on the East Coast are going, wow, that's great. And we're going like, yeah, it's every day. That's no big deal. But for them, going to England is no big deal. For us, it's like a major accomplishment. So, and then just to talk about Skip, from our point of view in Washington State, we have the aurora to have to deal with. So you think, well, we'll take the global route. We'll take the over the Arctic route to get there. Well, yeah, but we have a high level of ionization in the Arctic. So we don't get a lot of signal propagation through the Arctic, generally speaking. In fact, some people in Alaska, they actually point their beam antennas at the aurora and at the Arctic, so that atmosphere, so that they use it as a mirror to bounce into continental United States. So there's all sorts of interesting things that way. Okay, I'll after this one, I will talk a little bit about, ask for any more questions. So I talked about the temperature gradients between night and day side. And what this sets up is what's called a gray line. And the gray line is that basically the space of dusk and twilight, between morning twilight and evening twilight, because on one part of the world it's evening twilight and the other part of the world it's becoming daylight. And because of this, we see changes in the D layer, where the D layer is going away on one side and thinning out, and the other side it hasn't built up yet. And in that special area, you can have special propagation for those specific HF frequencies that's enhanced in that space. So it's north to south transition and it varies with the season. It allows lower frequencies to be reflected by the E layer, with optimal window being about 10 or 20 minutes. It's a very tight window. So if you get gray line propagation, it's a very tight window of 10 or 20 minutes where you can then go to these lower HF frequencies, the 80-meter band, for example, and use that to go much longer distances than you normally can, because the people on the other side of the planet are in an early morning before the D layer is really formed, and you're in a space in the twilight when the D layer is disappearing. And so then you can be able to kind of have that propagation going. And it's people who chase the gray line propagation, and it's kind of fun. And if you can do it, it's great. And it's kind of special. And the maximum usable frequency drops during the night and rises during the day with the changes in the F layer, which is what basically I said. So if you remember, we have in radio, we have what's called the MUF and LUF. The maximum usable frequency says that anything above this frequency, whatever that MUF is, will pass through the ionosphere into space. Anything, the lower usable frequency says that any frequency that's below the LUF will be absorbed by the D layer. So the active skip frequencies are between the LUF and the MUF. And that's what's happening when we talk about the D layer thinning out and it hasn't built up yet. This is a change in the MUF characteristics. I'll stop here and see if there's any questions. Okay.
I got a quick one, maybe.
Yeah.
With NVIS, does that have an effect on polarization?
You're still going to be elliptically polarized because you go through the ionosphere, and non-incident vertical sky wave is basically, let me see where I put that. Basically, the major amount of energy coming out of your antenna is going as close as straight up as possible. And so it's being reflected by the ionosphere and coming back down, so it's elliptically polarized. But because the angle is very sharp going up and down, communications is relatively short distance, like 600 to 800 miles in radius typically. Why would you want that on the HF frequencies? Because if you're doing emergency communications using HF, you don't want long distance communications. You want to maximize your communications with the people who are in the disaster zone. And so I hope I answered did I answer your question?
I think so, but I mean, the recommendation would be to have a horizontal antenna, I think, right?
For near vertical incident skyways, most of those antennas can be of one or two types. One is a relatively low horizontal dipole. So a dipole that's lower than its optimal height for having DX will give you, and we're actually going to show you pictures in a few minutes about that. And so the horizontal dipole that's low will give you a more 90-degree, more omnidirectional, most of the energy going straight up and down. However, you can also do other antennas. There are types of inverted Vs that will do the same thing as well. But yeah, low horizontal antenna will give you NVIS.
Right, but definitely not a vertical.
A vertical, no, because it's primarily a vertical, gives you a lower takeoff angle, so the more DX. Yes.
Right. Thank you.
Thanks for bringing that up. Other questions before we go on? We'll take a break in about 10 minutes. Is that all right with everyone? Okay. So let's just finish up this section on the atmosphere, the ionosphere. So solar disturbances, I can't speak today. They're either, wow, this is a lot of fun. Let me really get on the air, to, oh my, I've lost all radio communication. So that's the span of solar disturbances. It's either, wow, this is fantastic, or oh my God, all my radios are gone, or the power grid's gone down, whatever the situation is, how bad it gets. So sunspots are the temporary areas of reduced temperature. They're darker than the surrounding areas, and they're really a nice source of flux concentrations. And we love, as amateur radio operators, the higher the sunspot number, the better we like it, because it means there's more energy hitting the ionosphere because of those sunspots, more flux. The solar flare is the eruption of this energy and solar material when the magnetic field is disrupted on the surface of the sun. Again, it's going to release a lot of energetic particles. The energetic particles will ionize the atmosphere at a higher rate than average, and that can give us a lot more reflection that we love, or it can be so energetic that it basically shuts down the radios, the radio propagation. The coronal hole, a weak area in the sun's corona through which plasma can escape. So these are all things that can cause plasmas and energetic particles, etc., to erupt off the sun and head into the solar system. Some of it is glancing by Earth, some of it misses Earth completely, and some on occasion takes a direct hit to Earth on the side facing the sun. And that's what the CMEs are, coronal mass ejections. It's a large amount of material coming out. It depending on the strength of that and the angle it hits, it can be extremely disrupted, or again, make great surf. So ultraviolet and X-ray radiation impacts the Earth's atmosphere in about 8 minutes. And the D region is affected. It can be affected so much that you get radio blackouts on really high levels of intensity. However, that's the first effect. It takes about 8 minutes. But other material from the sun, other solar wind, energetic solar wind is coming from the sun, arrives about 20 to 40 hours later. And this increases the E region and the aurora. So if you look at space weather, you'll see that on space weather, you can see where they're plotting the aurora to be. And the more it comes down into the North America, the more you can have an energetic atmosphere that you can bounce more signals more readily and further from, until it gets to a point where it's shut everything down. So generally speaking, shutting things down is a very rare occurrence. So when there is a solar flare or a CME, oftentimes we do expect to have good E and F layer energy levels that allow us to take our radios and go further. Could be further because the ionization is so high it reflects more, and there's more energy passing, getting reflected back down rather than being absorbed, for example. And then, of course, the E layer means you reflect, again, if you get E layer reflection, you don't go as far. F layer reflection is when you get the furthest skip, because it travels at a higher altitude. So other numbers to understand, the SFI, it's about 2.8 gigahertz of energy coming from the sun. When you look at that on the space weather, 60 to 100 is relatively quiet. If it's 150 to 200, it's active, and the higher number, the more ionization radiation, as I've discussed before. The K index is a short-term stability of the geomagnetic field of the Earth. It's rated 0 to 9. 1 to 3 is quiet. 4+ is geomagnetic storm. 7+ is extreme. In the 10 years I've been, or a little bit over 12 years or so, I've been an amateur radio operator, I haven't seen a geomagnetic storm over 4. However, they do happen. It just, we've been gone through a solar minimum 24. Solar cycle 25 is better, but it's not anywhere near some of the other more energetic solar cycles that have happened. And as a lot of you know, solar cycles are 11 years. There are different types of cycles. There's 11-year cycles, 23-year cycles, and 100-year cycles of different things that are happening between the interaction between the sun and the solar system. And the A index is just an average of the last 8 K indexes around the world. where 0 is stable and 400 is disturbed. It's more historical than real time. If you really want to get a sense of things, you're going to look at the SFI and the K index, and that gives you more information when you're doing DX. There's a lot of information out on the web, internet for DX. There are places that where the ionosone, the radiosones are collected, and you can actually develop contour maps of the Earth, and you can see, oh, here's a contour. My contour line at 14 megahertz hits the contour line of somebody in Argentina at 14 megahertz at this right time. We should be able to talk to each other. So if you really want to get deep into this, there's lots and lots of stuff on how to plot out to get the best DX possible for the furthest distance. That's a separate course in itself. So, but I'm not that heavy into it that I study that stuff, but there are people who are, and they're the guys going to, they want to do the work all countries kind of award, and that wasn't something that's been interesting to me. So this was the space weather on the 28th. SFI was 150, which means it favors 20 meters. It's on the lower side of active. The average number was 21, which means it's relatively stable. K3 was low, so it's relatively quiet. And you can see here at the bottom of the screen on the right, the MUF at Boulder was 18.96 megahertz. Sometimes I've seen that down to 13 megahertz, which means if it's a 13 megahertz, you're not going to get a lot of great communication on 20 meters. So because it's at 14 megahertz. And so just some piece of information. This is, for those of you not familiar, this is one of the solar weather widgets provided by N0NBH. And this is the one that's posted on QRZ.com one of the sites I have a bookmarked. So come on in. So 2 more and then we'll take a break. This is what I talked about before, is we can see in the center in the red box, these are the different transmitting frequencies of WWV. And by the way, there are other countries that have their version of WWV as well. And this one transmits at 2.5 megahertz, 5 megahertz, 10 megahertz, 15 megahertz, and 20 megahertz. That's a really good approximation to our HF bands. And so because of that, when you tune into that and you can hear the signal strength of WWV is bad, that band is not going to be great for propagation. If you hear it really relatively strong, that band, HF bands around it are going to be better for propagation. So if I hear 15 megahertz is really strong, then I know the 20 meter band is probably going to be equally as strong to propagate. So that's a quick way of getting beacon information about propagation by listening to those stations. I have them programmed into my radio, so I just push them, and over the course of about 15 seconds, I get an idea of where I want to start for the day. And there is other information. This goes into detail. There's lots of information that's inside of these transmissions at certain times of the during an hour. The geo alerts are kind of fun to listen to. And so, sometimes just sitting there listening to the time ticks is you can hear the different other information that's being conveyed at different times of the hour. And then the other thing, there are different things on the internet that amateur radio operators have put up. This is an example of what's called the reverse beacon network. And this is a number of stations have voluntarily decided to post all the stations that they hear, and it gets plotted so that you can say, oh, who is on the, not only who's on the air and what frequency they're at, but you can also say, oh, there's a lot of stuff going on between, Germany and Russia. Well, I happen to be in Germany, so I know that I can start calling Russia. So you can start getting an idea of what the propagation like is during the course of time during the day, based on the different bands that everybody's sharing their information on. There is a whisper network, WSPR network, which is a number of amateur radio operators around the world who have essentially 200 milliwatt beacons on different frequencies, and they're always broadcasting those beacons, and there's someone collecting that information and posting on the internet to get real-time propagation maps. So there's a lot of resources if you look for these kind of things on the internet to help people figure out where should they go to get the longest distance contacts. So why don't we take a break here? It's 7:38. Can we get back at 7:50? We'll get it back 7:50 and we'll start the second part. Is that all right with everyone? All right, I will see you at 7:50. I'll stick around for a few minutes to see if anyone has any questions. I'm willing to sit here and take whatever you got. Okay,
Yes,
see you at 7:50.
Hi, David. This is Musa. I have a question for you.
Yeah.
On the signals that bounces off the ionosphere and it hits back down on Earth, when it goes down and hit Earth's surface, does it make a difference if it's water or if it's solid, the way they bounce back up? Or
Yes, it does.
Oh.
So it depends on a number of factors. What it, the material it's hitting, as you say, water, land, a piece of metal, it can then be absorbed or reflected, or both, partly absorbed, partly reflected. So yeah, that's all possible.
So when you are aiming for signals, if you don't want anything of it, if you want it to hit the ocean, for example, then you know that it's gonna go in certain direction further away than if you go east and it's gonna hit land. It might not. Am I correct? Or
yeah, well, yes, and most likely though, you kind of, I don't know, I can't speak for guys with super big, wonderful antennas, but I can speak for my experience, which is you want to maximize your antenna for the takeoff angle that works for you, that you want for the longest distance. So takeoff angles of and this is a controversial thing, but I'll just say it this way. Takeoff angles of 5 degrees to 30 degrees are really good for long distance communication, because it takes them longer to get up to the F layer, and therefore they have a longer distance that they're being reflected down. The reason I say there's a little controversy is because there is I'm just learning this. There's a bit of physics around the 5 degree area and lower that nullifies the advantage of the 5 degree takeoff angle. But it basically anything between 5 and 30 degrees is a good takeoff angle. And then the idea is really don't worry about if you're going to bounce off the ground or not. What you want to think about is, where am I putting the energy of the antenna? So not only takeoff angle, but if I have the ability to add a reflector to the antenna and a director to the antenna, parasitic elements they're called, then I can direct the beam to a better direction. And then I can optimize the geography of where I want to go, assuming I'm only going to go one hop. Okay.
Sure.
And then if I get more hops, great.
But with that, I'm thinking like being here in Washington State, Western US, most of the communication when it hits Europe, it's always traveling eastwardly. It never goes west and goes around the globe and back to the European continent.
Yes, it can.
It can?
Yeah, it can.
Okay.
It's called long path. Yep, it can.
Okay.
It's possible to be ducted all the way around the Earth like that. It's not generally doesn't happen, but it's not unusual. In fact, there are situations, rare situations, where you can actually hear your own signal coming back at you.
Oh, yeah, sure. Makes sense. Makes sense. All right. Well, thank you, David. You bet.
No
We'll
problem.
be back in 10 minutes.
Okay, great. Anybody else have any questions?
Can you tell us where we can find that solar page that shows the predictions or the current space weather?
Yeah, what you can do is go, and I'm putting it in the chat right now.
Great, thanks.
Put in the go to qrz.com, and you'll see that same diagram that I showed you a few minutes ago. If you click on that diagram, it'll take you to the main page for that space weather. Also, give me, I don't have my I never know what her website is, but if you put that in your search engine, you will find Tammy, who does one of the best space weather broadcasts in the world. She is famous. She's the space weather girl. And she does it as a real weather broadcast.
Nice.
So it's I think she puts it out every week. And then also there is a propagation. If you're part of the ARRL, you can ask them to send them the propagation bulletin once. I think it's once a week. They send out a propagation bulletin by email, so you can get that as well.
Great. Thank you.
Other questions?
I'm not seeing the links that you were talking about or the search term you were mentioning. Did I send that to everyone or just someone in particular?
I guess it was an accident. It didn't, somehow it moved. Hold on, I'll put it back in. Meeting group chat. I think that's where I need to be. I didn't realize somehow it moved over to somebody specifically. Do you see that now?
Yeah.
Okay.
Cool. Look up Space Weather Woman. I had a question, a couple of them actually. Speaking of background noise levels, I'm also in the Seattle area. I'm in Kirkland. And it's just so noisy that I can't hear people when they're calling back to me.
Okay. I will
Have
give you a little trick. Hold on a second.
Okay.
I was going to mention this, but you'll go ahead and do it now. Okay. There's another link for you. Here's a link, and there's two types. websdr.org and the other is Kiwi SDR. I use websdr.org. Find an antenna nearby. In my case, I think I use the one in San Francisco or Utah. And what you can do is on your computer, you'll see basically somebody has put their receiver with a really nice antenna online. And you can actually tune that antenna using a waterfall. And there's lots of different controls over the radio there that you can have with. And so let's say you wanted to call CQ at 14.2. You would set that up to be receiving at 14.2. You would be listening on your computer on WebSDR, and you'd be calling out on your transmitter. And that way you're hearing them on a really good antenna that's not in the noise area. And then because you're transmitting, you're getting out, they just can't hear anybody to talk to. Now you have a way of getting to talk to somebody because you're using someone else's antenna in a quieter area to listen. How's that sound?
Yeah, that's really cool. I actually did that. I did that. I went onto the Maui SDR and I heard myself. I found a spot that was clear on the Maui SDR and I transmitted on that on 10 meters from my HF rig. And I could hear myself in Maui. But then people started calling me back and I couldn't hear them on the Maui.
That's the old thing is that
but that's a good idea for San Francisco.
Right. They were hearing you were here and hearing your Maui because Maui's like one hop for us. But whoever was talking to you is probably from the East Coast or middle of the country. They need multiple hops to get to Maui. So so you couldn't hear them because your noise, if you didn't have the noise level where you were, you would have heard them. But because you're using Maui, you couldn't. But I'll tell you one thing that's cool about using WebSDR that way is you can adjust your audio using WebSDR to hear what you sound like and decide what kind of compression and things you want to use on your radio.
And this other question might be something, I don't know if you're going to cover these kinds of devices, but things like the QRM eliminator X phase and the MFJ noise cancellation bridges, these devices that have like a reference antenna. And then
I wasn't gonna cover that because it's kind of like a 201 level or 2301 level. But yeah, you can, because I need to get into how they do it. And some of the devices are using phase changes. Some of them are using the reference antennas to, where you have two antennas on your radio, one for receiving, one for transmitting, and then or a third antenna, and you can then use one to null the other. So I haven't gone that route. I have thought about that many times, but I haven't gone that route. If I had the time and was more adventurous, I've always had, especially with GNU online with software, it's possible to, basically this is one way of nullifying noise, is white noise, I can go off frequency to where I'm going to be, pull the white noise into a differential amplifier with the actual audio with noise frequency that I'm listening to, and I can then subtract one from the other to get the result, which should be a better signal. So I know how to do it in theory. I just am too lazy to build it. So, and that's the basis of noise canceling headphones as well.
Yeah, exactly. Yeah.
Other questions?
Okay, great. Thanks.
How's it going here? Is anyone how are we doing? Are we am I too basic? A good review? Something new? Is it something you guys are finding interesting?
This is Stephen. I would just want to say that out of all the YouTube videos and all the learning I did to get my license, this has been the most helpful information out of anything I've ever seen since I got my general license about 4 years ago.
Well, thank you very much. I appreciate that.
Well, I do have one question, and is there a way that these slides would be available after the class?
The slides, well, again, we're recording this, so it'll be on Mike and Key's YouTube channel. If you email me, I will send you a PDF of the slides.
Awesome, I will do that. Thank you.
Thank you, David. Excellent presentation.
David?
Yes.
If you send me the slides, I can enter them in on the Mike and Key website.
Oh, okay. I'll do that. So think about so I'll make this announcement when everyone's back as well, or towards the end. The slides will be available. I'll send the slides to Scott, who's hosting this on behalf of Mike and Key. He will post them with the video on YouTube so that you can get, or onto the Mike and Key, excuse me, on the Mike and Key website so you can get to them. So yes.
Well, the slides will be on Mike and Key.
Right.
The video will be on YouTube.
Yeah. I'll write that up.
Right.
Comment?
Go ahead.
David, Bob Triggs, W2IBK. Just wanted to say thank you. Very helpful. Very helpful. Much appreciated.
Good. Thank you. I appreciate that. And again, I'm feel free after the whole session. I take any constructive feedback. So if you say, hey, this didn't work for me, feel free to tell me why and how I can improve it. I'm always open to that. Okay, how are we doing on time? It is now 7:51, so it's time to get started again. And here we go. All right, what chapter are we up to? HF antenna basics. Okay, that's fun. Now we get, RF is just spooky. When you really come down, I like to think of antennas as somewhere between science and alchemy. That's kind of like the way I look at it. And not everything runs by the book because there's so many different variables. So key things about antennas is, and kind of like this is what I mean about alchemy, there are no perfect fixed antennas unless you plan on working one frequency in one band, because as you all know, resonance only occurs at one point on an antenna. Once you leave that resonance point, things will then be degraded. Now, there's an active thing I put into this number 1. Notice I say perfect fixed antennas, because there is a class of antennas that are not fixed. That is, there are antennas where you can vary the length of the dipole, like stepper IR, for example, type of antennas. You can vary the length of the antenna elements as you're tuning your radio. So it changes the resonant point as you tune your radio. A magnetic loop antenna, you are actually retuning that, you're adjusting that antenna for its best possible, well, that's not good. Just let's say with the wire itself. So there are antennas that you can adjust. They have motors, and as you change the frequency, they actually adjust their length accordingly. So that's why I use the word fixed antennas here. And also, getting power to the antenna is not the same as the power rating from the antenna. So oftentimes we talk about, and we'll get into a whole chapter on maximizing power transfer, but I want to make it very clear. Once you get the power to the antenna, that doesn't mean everything's going off the antenna. Some of it will be lost in different ways, or the pattern of radiation will be different depending on how the antenna was set up and the band that regarding to what band you're operating. Now, this one is kind of really weird. It took me a while as a young ham to understand this one because it sounded counterintuitive. And the more radiation resistance, the better. So you go, wait a second, what does that mean? It basically says the atmosphere is a load. And so the more the load, the resistance, that load, the more energy is being transferred to the load, which is the atmosphere, the better. So we always talk about the radiation resistance should be much higher than the losses in the antenna so that we transfer more energy to the atmosphere. Again, why things don't always act the way they do in the models is because everything around an antenna impacts an antenna. The quality of the conductivity of the ground, is there metal structures around the antenna? Is your car parked next to your antenna? You know, is there whatever is around the antenna interacts with the fields of the antenna. But always remember, a bad antenna is better than no antenna at all, assuming you're not doing something damage to your transmitter. You know, people say, well, that antenna is really just a dummy load. Well, that dummy load you picked up 15 stations on is not a bad dummy load then. It's better than having no antenna at all. So any antenna you can come up with that's going to be the optimal for you is the right antenna. And sometimes it's, you know, it's sort of like, I like to equivocate this to people who own boats. You own a boat, what's the thing you usually say? You want the bigger boat. You want the better boat. So it's always that way. Every time you get an antenna, you want the next best antenna. So, but the end of the thing, there's a lot of trade-offs here. How much can I afford? How much land do I have? How much things are interacting, et cetera, et cetera. All these things get into what antenna you're going to choose, but it's better to have an antenna than not have any antenna at all, because without antenna, you're not doing ham radio. And generally, you can easily make a lot of your own antennas. So this is a great, you know, not everybody can these days do SMD soldering and handle computer programming and build their own radios, but most people can build something of an antenna themselves. So that's kind of like one of the ways to kind of get some playing. And safety is always number one, and it's often also number two. So there's two levels of safety for an antenna. One is when you're constructing and setting up the antenna, make sure you're safe. And the other is, remember, RF safety is something we have to concern ourselves with at all times. Even if it's 20 watts, you want to think about what impact that's having and consider that. Even if it has no impact, take the time to look at the calculations and confirm it. Let's talk about series resonance. So here we have a typical kind of SWR kind of curve where we have impedance versus the frequency. And as we get to the resonant point of the antenna, remember, in class, I oftentimes talk about in a very loose way that an antenna is like a tuning fork. And tuning forks have only one resonant frequency based on their physical characteristics. Now, sound is not the same as radio frequency, but we can draw an analogy. Antennas are similarly. They have intrinsic characteristics because of the way they're built and their length and et cetera, that gives them a specific resonant frequency. And anything to the left or right of that is no longer resonant. It's going to have a less than optimal situation. So what is resonance? Well, technically what resonance is when the capacitive and inductive reactance cancel each other out, and what's only left is ohmic resistance. So if the entire wire system has 5 ohms and you hit series resonance, then you only have an impedance of 5 ohms. If you're off of that resonance, you're going to have a larger value of impedance because the capacitive inductive reactance have not been totally canceled themselves out. The left side in this graph, technically, the left side would be more capacitive and the right side would be more reactive or inductive, excuse me. Now I'm going to draw a difference here. Usually in a lot of classes, we don't use the word series resonance, but the reason I put it here is very, very specific. There is going to be something in this antenna where I'm going to switch to parallel resonance, and that'll have a very different characteristic. So I want you to keep in mind that we're talking with an antenna in this kind of normal antenna as a series resonance. So that's the point at which the antenna is basically optimized to receive or transmit a frequency. So let's start with dipoles. There are half-wave dipole here. We have 2 orientations, a horizontal and vertical dipole. Construction-wise, they're exactly the same. It's just that their orientation and their polarization will be different. You can see the formula down there, 468 divided by F, where F is the megahertz that you learned in class. And if you're ever interested, there's a whole article that's now been written in the last 5 years on where that number comes from, and the fact that there were probably 5 or 6 different numbers like that and where they all come from. So it was kind of, like a little history there's a reason for where those numbers come from. So just to review, current is maximum at the center, and voltage is minimum at the center. So the biggest voltage is at the ends of the dipole. The biggest current is in the center of the dipole. This becomes a factor when you start thinking about certain characteristics of things like end-fed dipoles and why they have huge impedances at the ends, is understanding how the waveform propagates across the dipole, which is where the voltage is minimal and maximal, where the current is minimum and maximum. Also, one of the things that's kind of another thing that took me a while to understand is, it used to drive me crazy because I didn't really understand, how can someone use a metal boom for a Yagi beam antenna? Wouldn't that short things out? Well, when you think about it, the director element of a Yagi is a dipole, and the current is the voltage is at basically 0 at the center. So you can't short out the boom because there's no voltage there. And that's how come they can get away with using a metal boom on a metal Yagi, because at that point there is no voltage if everything's built right. We haven't gotten to Yagis, but there's a little trivia there. So one of the things I want to point out is here on the right, and you see that vertically oriented dipole, wire dipole. It's suspended by a mast or it's suspended by trees, whatever it is. But you notice the feed line here comes out at 90 degrees. It's perpendicular to the feed lines, perpendicular to the active elements of the antenna. That is what you do for a vertical dipole. You want to minimize the interaction with the feed line. You bring the feed line out at 90 degrees to the active elements for a number of feet, and that minimizes the interaction with the transmission line. So just if you ever do a vertical and dipole, that's something to just keep in mind. Okay, radiation patterns in free space for dipoles. Basically, we're looking at a donut, and you can see the one here in the top middle. It's been cut away, and now we can see the two lobes of the elevation angle. If you see a normal general 2D plot, you're taking a slice through that dipole, and you can see that slice of the elevation angle of a dipole that's up at half a wavelength in elevation, and you can see it radiates in all directions as well. And again, you can see less energy is going straight up in the air because this dipole that we have on this sheet is at half a wavelength in height, which means it's more maximized for DX operations. And you can see that when you have vertical dipole, you have a different orientation, and therefore you have energy moving in a different way. Now let's talk about impedance again. Now at the center of a dipole, the impedance is, we often use the term 50 ohms. It's actually not. If we looked at an ideal dipole in free space, it's more like, at the right height, it's more like 72 ohms. But for all intents and purposes, we consider that a 50 ohm situation. But as we move away from the center point on a dipole, the impedance increases as we go further down to the right, and this unbalances the antenna currents. A lot of people who learn about dipoles, or teach about dipoles, don't talk you to the fact that this is unbalancing the currents, because it gets really complicated. I'll just say that it may not change the way you think of these things, but it does at some point make sense when you get to certain types of antennas, that makes total sense. So in this case, as we move to the right, we are going to unbalance the antenna. And so on an off-center fed dipole with a ratio of 67 to 33%, that puts the feed point at about 200 ohms at about 30 feet in height. And so that's not 50 ohms. So we have to think about what does that mean? We don't have 50 ohms. What's it going to do to our system? Why would you even do that? Well, it turns out there are some interesting characteristics of going off center. And the interesting characteristic is it tends to make the antenna a little bit better for working at different frequencies. So remember, that 20-meter dipole antenna is really only optimized for 20 meters. Does it propagate on harmonics? Of course it does. Does it propagate on odd harmonics? It'll radiate something. But it turns out that when you use some of these other dipole forms, you may decrease the efficiency at the optimal point of 20 meters in this example, but you then increase the ability to propagate at other frequencies more effectively. So if you take the off-center dipole to the furthest extreme, you get an end-fed dipole. And now at the end, you're seeing 2,500 to 3,000 ohms at the feed point. Remember, your radio only wants to see 50 ohms, but you're at 2,500 to 3,000 ohms at the feed point. And so this is just an extreme example of you can keep moving the feed point until you're basically on one end of the dipole. And this changes the characteristics of propagation across the different amateur radio bands. So it's kind of a way of, some people use it, like I said, as a way to get a little bit better performance across all the amateur bands by sacrificing the performance on the amateur band it was actually built for. So that's one way of looking at it. But again, anything will propagate. It's just what pattern is being created and how much energy is being transferred into the atmosphere that determines whether it's efficient or not. So here's the horizontal dipole radiation pattern. It's affected by height. And so look at the one that's 1/8 inch, 1/8 of a lambda high. So lambda is the wavelength. So it's 1/8 of its 33 feet for a half wave antenna. 1/8 or let's say it's 60 feet for an antenna for one lambda, then 1/8 of that would be the height of the antenna, and that would give you a pattern like this. And so what do you see? Omnidirectional, lots of energy spread out, but very little energy concentrated to the ends or to the sides. More of it is equally spaced. So you're going to see this as more of a Nevis operation. It's going to put a lot of the energy more in the straight up direction than the side directions. You get to quarter lambda in height, you're starting to see it kind of become more elliptical and flattened, which will put more energy towards the sides than it was in the 1/8 inch waves. And then when you get to half wave high, which for 20 meters is about 35 feet, now you have, in free space, in the ideal situation, you have two distinct low angle lobes. And so now we're terrible for doing local communication. We are optimized to do long distance communication. So I have a friend who used to live in Lake Stevens. We could never talk to each other on HF because both of us have antennas that were optimized for DX. So we were just jumping over the top of each other. We couldn't talk to each other. And so you get to 5/8 wave, and you can see the patterns are changing as we get higher and higher. And each of them has its advantages. So you can see a 5/8 inch lambda high dipole gives you Nevis operation and long distance operation. So you can choose kind of where you want the energy to go based on the height and what you want to do. Of course, this is all about free space. So I'm going to stop here. Does anyone any questions about this? Yes, I mean half wave antennas. Thank you for asking the question. Any questions? Okay. So this is one of those fun things that we've all learned, and then a lot of times it gets lost in the details, but impedance changes with height. So and this becomes important as we drop the antenna closer and closer to ground, you can see the impedance is dropping. And if we raise the antenna further up to a certain point above above lambda, we're going to increase the impedance. So let's take that off-center fed dipole again. At 67% and 33%, it's at 200 ohms, and I said at 30 feet. Turns out that when you get up to about 50, 60 feet, it becomes about 600 ohms at that location. So it does change with height. If I bring the antenna if I elevate a vertical antenna at let's say 50 feet, it's going to have, around 50 ohms impedance. As I bring it down to the ground, it's going to go down to 25, 32 ohms, which typically a vertical antenna towards the ground will get to about 30 32, 35 ohms impedance. So this becomes important to know, because as you're working with antennas, you need to start thinking about, how am I going to match these impedances? And making sure that you do that so you have the most effective energy transfer you can to the antenna. So another one that's very popular is trap dipoles for multiband antennas. And then these are wonderful because they're basically switches. Now, remember I said I'm making note that this is series versus later on I'm going to talk to you about parallel resonance. This is about parallel resonance, which acts completely differently than series resonance. So let's say we want to have a 20 meter and a 40 meter antenna, but it's only one dipole. We only want one length of wire, well, on two sides of the feed line. We don't want to have two different antennas. We want to have one antenna served by one dipole. So we need to create a trap. One of the options is we can have a trap, which is a bypass filter. And that trap is made of an inductor and a capacitor. It is a LC network. So we built a 40 meter dipole, the full length of that wire for 40 meter on both sides of the center feed point. And then we insert a trap basically at the spot where a 20 meter antenna would be. So if you think of one leg of a 40 meter dipole, it's about 33 feet long. If you think of how long is the leg of a 20 meter dipole, it's about 17 feet long. So you would put a trap at 17 feet, let's say. And what would happen is that as we get to 20 meters, the parallel LC circuit's impedance begins to rise. So when I hit the 20 meter band, anything beyond the 20 meter band energy is stopped at that trap. So the antenna was only using 16 feet on each side of the dipole, effectively. So in other words, the radio saw only a 20 meter dipole. But let's say I switch to the 40 meter band. At that point, with a parallel LC circuit, the impedance is relatively low and the signal will pass through the trap and will use the full length of the wire to create the 40 meter dipole. Now, the problem with traps, because there's no free lunch, is it does have some power losses associated with it. But it has the advantage of having one antenna dipole be used for multiple bands. And here's an illustration of a 5-band trapped dipole. And you'll see this in the ARL antenna book, I think, is where this has been put. And this has been a very common method for having one dipole serve multiple bands. And this is automatic band switching. So because these switches automatically close or open depending on the frequency, there's nothing for you physically to do. It automatically happens for you. Okay. Any questions here?
I have a question to go back a little bit on this is Musa, by the way.
Yeah.
To go back on the elevation and height of the antenna, you refer to the ground or the sea level. Which one makes it better?
So the ground is not a great conductor unless you're on some salt flat. Ground is not a great conductor. And if you look at antenna modeling software, they'll ask you, do you want to model this with bad ground, average ground, great ground? Ground being earth. And then salt water, if you are near salt water, relatively close to salt water, that has a large effect on your ability to have efficient propagation. So people who are doing work near a beach often will have much better propagation because they have a better, quote, earth ground than for their antenna. Now, not all antennas need an earth ground. So vertical antennas that are on the ground need an earth ground. Elevated antennas don't need a ground. Unless the ground is used as a reflecting element. And that all depends on what height you're at. Okay.
So may I ask, add on to the question? So you're above 2,000 or 3,000 feet elevation. Does that make a difference than if you are 200 feet elevation?
Well, it depends on how you're asking the question. If you're saying I'm at 3,000 feet, but my antenna is 30 feet above 3,000 feet, then the ground is still 30 feet above the antenna.
Yes.
However, relative to the antenna, but do you have better space wave propagation at 3,000 feet? Yes. Do you have other factors that are better because you're higher at elevation? Yes. But relative to the antenna and ground, it's still the same 30 feet.
Same 30 feet. All right, thank you.
Okay.
That's clear.
Okay. So here's a ground mounted vertical with a radial system. Now, radials don't need to be, when you have a ground mounted vertical, the radials do not need to be tuned. So there's a lot of data on this. There is a lot of old data and there's some new data, but the current data is you don't have, the ground detunes the radials, so you don't have to have the radials cut precisely for the frequency you're operating. One of the easiest things to do is what's the lowest frequency you're operating your vertical ground mounted antenna? That's the length of the radials you should go. Don't get crazy on making them absolutely cut tuned properly to the down to the inch, because it's not going to make a big difference. What makes a big difference is the number of radials you have on the ground. And because what you're doing is you're creating a return path for the antenna's current, and the ground is a terrible return path. So you're using wire on the ground to supplement the ground and get a better return path. So how many radials? Well, if you look at the old school stuff, it says you have to have 120 radials of a certain length. A lot of research has been done where that came from, what happened there, how it worked. It comes down, and the ARL antenna book goes into this in well detail, some really good graphs on it. And it comes out that, yeah, you would get some benefits from 120, but there's a point of diminishing returns. And that point of diminishing returns, depending on what your economics and your space, is about 32 radials. And ideally, and even 60 radials would be probably definitely the point of diminishing returns. You could go to 120. That'd be fantastic. But 60 will do you good enough. Now, with 16 radials, each with a length of 10% of a wavelength, by the way, the number of radials, if you look up the data and how long they are, is relative. So if you have 32 radials, they have a different length than less radials. And you'd think it'd be less radials would be longer. It's the other way around. But 16 radials each with a length of about 10% of a wavelength results in a 3 dB or half power loss at the antenna. Now, that sounds bad. In some cases it can be, but in most cases it's not so bad. So you're operating, and I will tell you, it's not so bad. You can live with that. But anything less than 16 radials, you have a lot more losses. So you'll see that people, if you buy a commercial radial plate, you'll see they come with 32 holes. And because that's what that is where they think is as most wire that someone uses. And if they want to use 64, they would double up and say, in this picture, you can see on the left, they've doubled up on the wires, on the radials. And you can see on the right that they have, I think they may have the 60 radials on that one. By the way, you see that they've curled up the coax on the bottom of that antenna. And what that is called an ugly choke. And they're using the that coiling to act as a way of cutting off the common mode current that may be in the coax sheath on the shield that may be coming back down the antenna as SWR. And so they're using that coil as a slightly good a slightly okay choke to choke off the RF coming down the braid. So 32 rails is about a loss of 1.5 dB and 60 is 1 dB loss. But here's the thing I want you to keep in mind. There's a lot of advertisements out there that say this vertical antenna needs no radials. Don't buy that. All vertical antennas need radials. That's just science. If you want to maximize your ability to function as how that antenna function, you must have radials. And if it's an elevated vertical, it needs counterpoise. So counterpoise we'll cover in a second is basically a radial that's now in the air. So a radial in the air is called a counterpoise. A radial on the ground is called a radial. So, and let's see, I don't know if you guys can see this. Here is a quick and easy radial system right here. And it's basically a flange for a wastewater system. And it's 2.5 inches in the center open for a mast, and it has tie points for a radial, and you can double up and have 32 or 16, or if you want, whatever number you want tying off. It's just a quick and easy way. It's copper on the outside, as a conductor to put them all together. So there's all sorts of ways of making quick and easy radial systems for your antenna. And here's the ground vertical, here's a quarter wave vertical antenna. So you've used these a lot for 2 meters and UHF. But for HF, ideally they need to be elevated at least 6 to 7 feet above the ground. It turns out that using counterpoises, elevated counterpoises for these antennas, at least 4 and better is 8 for each frequency that you're using, is actually more effective than ground radials on a ground antenna. So by elevating the antenna up 6 or 7 feet, having elevated radials, you will then have more effective vertical than if it was on the ground. However, there's a difference. Remember I said on the ground system, on the ground-based radials do not have to be tuned. But for a vertical antenna that's elevated, they have to be tuned. So that's the difference. So if you want to use, let's say 20 meter, 16-foot quarter wave vertical antenna that's elevated for 20 meters and the harmonic of 10 meters, you would need 16 radials that are tuned, 8 for 20 meters and 8 for 10 meters to get the most effective propagation from the antenna. Could you get by with only the 20-meter radials? Absolutely. Would you have the most efficient antenna? No. Does it matter? May not. Remember, you could decide what efficiency you want based on what you're trying to do and your economics. Vertical antennas have generally low takeoff angles. However, because man-made noise tends to be vertically polarized, they tend to pick up more man-made noise. The feed point, if you were to come straight out of that antenna with radials, that would give you an impedance in the ideal situation about 35 ohms. However, as you droop those radials down, the impedance will start to approach 50 ohms. Why? Because you're approximating a horizontal dipole. The reason the antenna begins to go down towards 50 is that you can see it becomes closer and closer to what a horizontal dipole looks like. And that's why it goes to 50 ohms. Okay, and just to finish up here, there are, like I said, other types of dipoles. A fan dipole, if you have the space, a fan dipole is a very nice antenna. There is basically it's, if you're working in this case, in this picture, 3 different bands, you have 3 dipoles all tied to the same feed point. Ideally, these wires should be coming off at 60 degrees to each other, or not all in the same plane, so that you have less interference with each other. And what happens is you can send up the energy to this feed point for 20 meters, and it would go to the maximize the 20-meter dipole. To 10-meter dipole length, it would maximize for the 10-meter dipole because the energy will take the path of least impedance. And so that's what's called automatic band switching. If you have the space, it's great. Oftentimes people will put these all in the same vertical plane. It makes it harder to tune, but because there's more interaction between the wires, but it will work. And then we talked about the off-center fed dipole. This off-center fed dipole is called a Wyndham on the right side. It's designed with the assumption that there is a lot of SWR because we have unbalanced currents. We're going to have a higher SWR and off-center fed dipole standing wave ratio, which means that we're going to have energy coming down the braid. And what the assumption is here is that that energy will radiate. And so that energy that's on the braid will radiate as a vertical radiator. And then we put a line isolator down there to cut off the energy and prevent it from going back down to the transmitter. So this is called a Wyndham off-center fed dipole. And the one on the left is a folded dipole with a terminating resistor. And these tend to be pretty broadband for their application. And they are, they have to have a very special resistor to do this termination. And they're very effective. I think I saw last time, it was about years and years ago, I was at the Vashon Island Fire Department teaching a class, and I think they had a folded dipole with terminating resistor up for their operations.
Comment?
Yes.
Sorry to interrupt.
No problem.
Somebody here on a microphone is broadcasting a Morse code practice session of some kind. So somebody in the audience has got something playing.
Okay, I don't hear it, but if you are, then so everybody make sure you mute your mics until you have a question.
I don't hear it.
Okay, well, we'll see what happens. Okay, by the way, any questions on the antennas we've talked about?
Yes, I have a question real quick.
Sure.
the off-center fed dipole, what is a good application for that? Because I am in Paulsbo, and I basically am probably about 60 to maybe 80 feet above sea level. So I'm basically across the street from the sound. And somebody had mentioned at our club that the only way to get a signal out is to bounce it across the sound and get it to come back in order to get a signal, because I'm at such a point that the top of my house is literally at highway, I guess it was 3 and then it turns into, I guess, 305 or something like that to go to the Hood Canal. But like the road is literally higher than my house level.
Okay. Well, you're in the valley. Okay, got it. So, well, I think that if we're going to just talk dipoles for a second, so obviously if you put your dipole on a really, really high tower or two, it will work. It'll work just great, right? But who has the ability to put up a 200-foot tower? So one thing to think about, I'm going to take this off the presentation mode for a second. And because I want to be able to draw to answer this question. One thing to do is you can take your dipole antenna, whatever kind you want, and make it a sloper.
Okay.
And slope it if Hood Canal, wherever the open spot, because your valley has some sort of open spot that you're looking down through, whether it's down the Hood Canal itself. Was that Hood Canal you were on, or is that what you said?
Yes, I am probably about 2 miles from the Hood Canal Bridge. Okay, so if you've got I'm just not knowing your property or anything, here's my speculation. If the Hood Canal if you're parallel to the Hood Canal in that direction, which means you're looking straight down the shoreline of the Hood Canal, then you can set up a dipole sloper, and that'll put the energy in that direction more than anything else. And it'll have an angle of takeoff that will get you up into the ionosphere. And that would work. You could try that. That would be up on a mast, of course. And, you could get a 35-foot mast or something to put that on. And this should be about 7 feet off the ground at least to keep people from knocking into it. And it's fed from the center, just as I showed you before. It can be fed from the center. And you could use an off-center fed dipole. There's no problem doing that. It works just as fine in the sloper configuration. And try that. That's one way of looking at it. I hope that, without knowing your property and being out there, that's probably a quick off the cuff answer. Awesome. Thank you.
Okay. And I'll just stop for a second. Does anybody have any quick suggestion for him?
Well, David, I have the question. Maybe you will answer it. I'm not sure.
Okay.
So on the dipole, does it have to be in a straight line, or could it go around the house perimeter, for example, or in multi-directional from the center fed going one way?
Yes. So everything, remember, everything becomes different. Anything can work, but everything becomes different. So I'll draw an antenna right here. This is a type of dipole. It's not uncommon. This is a horizontal dipole. It's a half square dipole. And this is what it looks like from the center point. And you can do that. You can even do things like, I don't know how fast I can draw this, but think of here's another type of antenna that's a dipole. And I'm going to just try to do this as quickly as I can. Oops.
Should we be seeing what you're drawing? Because I
Oh,
can't.
I'm sorry. I didn't realize it stopped sharing. Okay. Let me go back to share. And
Oh, I was seeing it just fine until you just now
Oh.
switched back.
okay, well, I thought she said she didn't see it. So now you can see it, right?
Yeah, the line is just pretty skinny.
Okay, hold
but
on.
I can see it.
Hold on. I will fix the lines.
I can see it.
Okay, good.
Because I'm about 8 miles down the canal from where he is. in a hole below the road. Same problem.
So you can actually even do this to an antenna in different orientations. This is called the meandering dipole, and it's a way of shortening the antenna. There is also, you can zigzag it, you can do anything you want. Again, the propagation change, the pattern of propagation will change, but if that's the best antenna you can create for your given situation, that's the right antenna for you. That's the best way I can answer the question. How's that?
Thanks, Dave. And then this is top view, but if you go on horizontal view, one side could be higher than the other side, up and down.
Absolutely. I mean, any way you want to, yeah, I mean, I'm not quite sure. You can lay those, antenna can be in any horizontal or vertical or combination configuration you want. It just changes the propagation and impedance pattern.
Okay.
It changes the antenna radiating pattern and the impedance, but it still functions. So,
thank you.
Okay.
Thank you. That's good.
Okay.
Thank you, Dave.
And I'm going to put back into slideshow mode so everybody can still see the screen, I assume.
I got one more question real quick.
Sure.
Going back to propagation, will the radio waves bounce off of water?
Yeah, well, yes. So the Hood Canal is salt water. So because you're near salt water, that will start affecting in a positive way the far field of the antenna. It doesn't necessarily mean you can predict if it's going to bounce. I would rather you say the word is enhanced. Because I don't know, I myself couldn't tell you what's really going to be happening because without knowing a lot more details, I would just say that salt water helps the far field of an antenna.
Okay, because I'm from the South in Charleston, South Carolina, and we really don't have to deal with any of these mountains and stuff like that. We can just shoot stuff as far as the eye can see.
Well, all I can say is that once you get your antenna up and start making some really good contacts, you email your friends in South Carolina and say, you want to know what real propagation, artistic, and ham radio skill is? Watch how I do it.
That's right.
Anybody could deal with a flat plane.
Exactly. Thank you, sir.
Okay. Other antennas. Here we have on the left a Yagi antenna. Again, can you build a Yagi antenna for HF? Absolutely, you can. They're big, but you can. In fact, Mike and Key for field day sets up two 40-meter 7-element Yagi antennas, one north-south, one east-west. It takes the guy a whole day to put it up, but they work very effectively. But most people have, a lot of people have the commercial, not a lot of people, but people buy oftentimes the commercial 10, 15, 20-meter trapped Yagi antenna, where they use traps like we described before, so that you can use one Yagi to handle 3 bands. But it's big. I mean, think about the bunch of radio wires for each of, basically for each of these elements on the ground. And I can spread this out for 20 meters, and I can have a reflector, which is 5% higher than the director element. Reflectors are usually 5% longer. And then I can have my vertical, quarter wave vertical, active element, and then I can have 2 passive directors. I can put that on the ground and make a beam antenna on the ground. And that'll give me the energy coming off to the side more than coming off from the back or omnidirectional. I can also build what's called a phased array antenna, where I have 2 elements in this case, and I've put in a delay line. The left side, you can see, says 22 degrees if you can see it, and the right side says, I think, 15 or 14 degrees on the right side. That becomes a transmission delay line. And because there's a delay between one element and the other, it causes an algebraic shifting of the waveform so that it now becomes sending most of the energy to one side over the other. So in this case, it will send more energy to the left than the right, and it operates like a beam antenna. And you can put, and in some DX expeditions, we'll put 4 of these arrangements up, and they'll have a switch. So they say, oh, this time of day I want to go east to west. This time of day I want to go north to south. This time of day I want northwest. This time of day I want southwest. And they can change with a switch which antennas are phased in and out so they can actually have a directional beam antenna by using a phased array. So there's lots of different choices of antennas. And by the way, these all work at any frequencies. So I shouldn't say, you can design them on their length and width and characteristics. So not only work on 80 meters, 20 meters, 2 meters, 220 megahertz. The concept is always the same. It's just the physical characteristics that are going to change. So there's basically all sorts of antennas are possible. This is just a small fraction of all the possible antennas one could build. But if you're going to do antennas, you got to have a friend, and the friend is the antenna analyzer. And typically with antenna analyzers, they can go from really, really cheap, like the Nano VNAs, which are about $50. By the way, they're really good instruments. I happen to like them, and I own one. I've also owned the Sender device as well at one time, which I basically preferred the VNA, so I got rid of that. And then probably the best, one of the best devices in average expense is the Rig Expert. So we go from 40 meters on the left to about 250 meters on the $200 to $350 on the right, just to give you a sense of scale. And so, but if you build antenna, these are the really more than nice to have, and even better, they're nice to borrow. So if you know somebody who has the expensive stuff that does everything, it's nice to be a friend to that person. And they can be used on antennas. They can be used to test coax, to test chokes. Impedance transformers can be tested, and inductors. They do a lot more things than just measure resonance and SWR. And remember, SWR and resonance are not necessarily the same point at all times. You can have a very resonant antenna that has resonance at 14.2 megahertz, and its SWR could be 5. And the lower SWR could be somewhere else, but it doesn't necessarily have to be at the resonance of the antenna. It's all different factors involved. So a nice guide, it's a nice guide antenna analyzer to have if you're doing anything, like if you want to see SWR, you want to work at Smith charts. We're not going to go into Smith charts. If you want to do reactance scan and plots and other things, they're really nice instruments to have. So if your thing is you build one antenna and it's good for life, don't buy one, borrow one from somebody. Have an antenna party. Have people come over and help you, and one of them has an antenna analyzer. That's always nice to have. But if you're like me and you like to play with antennas, then I own a Nano VNA because I get a lot of use out of it. Okay, maximizing power transfer. We're on the home stretch, people. It's 8:30, so we're doing well. I'm going to go. Any questions before I go on the next chapter? And we have one.
I have a quick question, just as your opinion in general from, this is a whole area that I need to learn a lot more, but can you give a very quick, your opinion about magnetic loop antennas in this context?
Yes, I love magnetic loop antennas. In fact, I have a capacitor over here that's been sitting on my table for 2 years waiting for me to build one. So here's a quick answer to magnetic loop antennas. They're fantastic. Okay. And they're the worst antenna you can ever have. So, and here's why I say it that way. First off, if you want to nullify noise, magnetic antennas are really good because they have such a tight bandwidth. Because they have a tight bandwidth, they have high rejection for noise outside of that bandwidth. So that's really one of their good functions. The other thing is, most people who build or sell magnetic loop antennas sell you or build the worst possible kind. So what makes a magnetic loop antenna efficient, and by the way, if you look at what people say is efficient for magnetic loop antenna, they're wrong, because anytime they say they're less than 50% efficient, it's because they have the wrong design. Magnetic loop antennas are really efficient if they're designed properly, which means, and here's the kicker, if you've got a tube diameter or equivalency tube diameter of about 2.5 inches in diameter or bigger, they're very efficient. For the frequency that you design them, they could be over 80% efficient. But guess what? Most people are building them with coax, which doesn't have much diameter, or small, thin tubing, not enough diameter. So there's a lot of losses in that magnetic loop antenna because they're not built correctly for the design. And so you want to spend $300 for a commercial magnetic loop antenna and a controller, if you're lucky to get one for that price, and you've got it, it's built out of coax, it's going to give you very little energy output versus its losses. So they're wonderful antennas, got great Q, good for noise reduction because they have such a tight bandwidth. You need to be able to tune them for every frequency essentially you're going to be operating at when you operate them. And if they're designed properly with enough diameter, they have sufficient energy transfer to make them very efficient for a compact size. But when you make them with the tubes that are too small then it's just not going to be efficient, and you're probably, wasting a lot of energy. That's my quick opinion.
Thank you. If I can ask a follow-up question, but not to make this too long, but just your initial feedback. The reason I'm asking is I live very, very close to high voltage lines. What makes me afraid that I would have very low, very, very high noise here, most probably. And I have a very strong HOA with very strong rules that makes me afraid that I will not be able to do much. And that has helped me back to do much, because before going outside, I would like to practice at home, and I feel spending money on something that I would not be able to practice makes this not very attractive.
So
would we trying with a magnetic loop, with a good one, would this make sense to spend on this and try this out, or is it just a wrong approach?
It might help you. I wouldn't start there because I would think about some other things. Do me a favor, email me with the question.
Yes.
Remind me we talked. I will make you a cheap suggestion to try things out with, okay?
I will do that. Thank you so much. Thank you.
All right, let's talk about maximizing power transfer.
Sorry, Dave, can I interrupt for a second?
Sure.
To follow up on antennas, Squallow, 6 meter, 10 meter.
Ah, yes.
And with the technician, and I don't want to go into a very heavy duty on the other band. Is that good enough? And can we run SSB with those, or how do they work? Question.
If I'm from, yeah, the square low, which is a kind of like a horizontal Moxum in a lot of respects, if I remember correctly.
That's right.
Yeah, you can. They're very effective antennas. They're monoband antennas generally. So if you're a technician, you would build it for the 10 meter band essentially. If you want to operate SSB on 10 meters, that is.
That's right.
And
I already built one for a 6 meter. I just want to know, comparing. Stick with these. Don't go into the higher antennas if you want to stay on.
I think that if you're having fun with the Moxum at 6 meters, build yourself the square low at 6 meters. Build yourself a square low for 10 meters. Go see how.
That's what. Okay.
Go enjoy yourself.
All right.
All right.
Thank you.
So we want to get the maximum power to the antenna, right? We have let's say 100 watts coming out of your transmitter. We want to get 100 watts up to the antenna. So, by the way, the left side is just my joke. I was trying to make a joke on some diet programs, but I don't know if it came through. So, so maximum power transfer occurs when the impedance of the source, that's the transmitter, matches the impedance of the sink, which is the antenna. So if it's a 50 ohm impedance that coming out of the transmitter, you want to see a 50 ohm match to, you want to see the antenna match to 50 ohms. That gives you maximum power transfer. But even with uniform impedance across the transmitting system, there can be power loss from coax, fittings, and switches. Also remember, in the ideal situation, if we want to go at the most ideal situation, we know that the impedance of the antenna is only good at one frequency. When we move off that frequency, the impedance will change because of the resonances being changed. But we talk about dipole as 50 ohms. We're just going to generalize that antenna is that many ohms across its bandwidth. Now, getting maximum power to the antenna is only part one. And now you heard me talk about this before. Maximizing radiating pattern and energy is part two. So not only do you want to get the antenna to have the full maximum energy there, we want to make sure that antenna can radiate as much energy as possible, the best radiation resistance. So for example, having a vertical antenna with the coil at the bottom of the vertical antenna, and the antenna is a ground mounted antenna, means that because the coil is low to the ground, it has a lot of losses to the ground. So you see a lot of PODA and QRP antennas where the coil is close to the ground. They work, but there's a lot of losses. How do you prevent some of those losses? You move the coil further up the antenna. So if you move the coil to the middle of the antenna off the ground, you'll have less losses from the coil radiating to the ground. However, as you raise the coil up the antenna, the inductance needed for the coil goes up. Just so you know, there's all sorts of other things. And I won't go into, I purposely decided I wasn't going to go into things like the coil and a capacitive hat and how to interplay off those two things. That will be a subject for another time, I think. But just understand that it's not only about getting energy to the antenna, it's making sure the antenna has the best possible way of radiating that energy. So a ham stick, people say ham stick is a dummy load. Well, kind of is. There's a lot of energy loss from the coil being near the ground. But does a ham stick still radiate? Absolutely it does. Will you make contacts? Absolutely you will. Will you get them all the power going to the antenna? No, some of it will get absorbed by the ground and by the coil. So just so you keep that in mind. So what's the difference between reactance and impedance? Just to review, reactance is the opposition to current flow from capacitors and inductors, and it varies with frequency, versus impedance, which is all of the resistance to flow, which is both the capacitive reactance, the inductive reactance, and the ohmic resistance. Okay, so that's when we talk about reactance and impedance. That's why we talk about impedance with an antenna system, is because we're also including the ohmic resistance as well. We talk often about reactance when we're talking about traps and other parts of a tuning circuit. We're talking about reactance, usually only. Now, everything has intrinsic resistance, just to say that off the bat, but we're really talking about the larger resistance in these systems on the antenna. So here's a weird fact. This is trivia for the day. If someone goes into a bar and you want to win a beer and they know something about physics and electronics, this is a good trivia question. Even a resistor has reactive components. So for example, at high frequencies, the terminals between the resistive material, the resistive carbon, for example, becomes reactive. It's like a capacitor. It starts acting like a capacitor. So understand that if you're testing a resistor with an antenna analyzer, and you're sweeping across all the high frequencies, and all of a sudden you see it's no longer 50 ohms, but varying with frequency. That's because you're at a high enough frequency where the leads themselves are becoming reactive. So just keep that a little trivia for you. That'll throw people off. At the next time you're having a ham meeting, at a club meeting, and you bet someone over a beer, they won't believe that you're correct, but you can say this. So next thing is this where I'm at? So impedance matches means it's great. So you can see on the left side, we have an output impedance of 50 ohms for the transmitter, the coax is 50 ohms, and the antenna is 50 ohms. So we got a match, right? Now, if we have 72 ohms at the antenna and we have 50 ohms and 50 ohms at the transmission line and the output, technically that's not a match. Is it close enough? Probably. Are you going to have much losses? Not a lot, but it's technically not a match. So we won't get maximum power transfer on the right, but technically in this illustration, we'd get maximum power transfer on the left. However, so let's talk about mismatch power. So here's an off-center fed dipole again. We have the 200 ohm impedance at this location, but the coax and the transmitter are 50 ohms. That is a mismatch. So what happens when we have a mismatch? The power has to go somewhere. So this impedance mismatch is like light hitting a mirror. So the larger that mismatch, the more energy is reflected back. So you can see that we have a small mirror on the top example. Most of the light's getting through. The bottom example, the mirror is much larger, and so a lot more energy is being reflected back to the source. So this reflection is called the standing wave. And the ratio between the energy that got through to the energy that got reflected back is called the standing wave ratio. And so that standard wave ratio is an indication of how efficient the power transfer was. The higher the standing wave ratio, the less efficient the power transfer was. Some of the power has been lost by being reflected back. Now, let's continue this idea. Let me stop here. But actually, is this okay? Does anyone have any questions about this? Okay.
I have a question.
Yeah.
Sorry, Dave. I was going to ask you on the SWR, the difference between high frequency SWR and VHF SWR, are they same?
The concept is the same. There's still a ratio. There's still a standing wave. Yep, just
Okay.
a standing wave
But
with different frequency.
But the equipment, because I was watching on the on the VHF, there is no what do you call it? Output, backward, or reverse, or what do you call it? Reflected.
Reflected.
Yeah, but on the high frequency there is. And if you have a machine to measure one, can you use it to measure the other one, or they're not the same machine?
No, you need the machine should the SWR meter you're using needs to have a range compatible to what you're measuring. So there are a lot of ones that are SWR. A lot of people are more concerned about it HF than VHF and UHF. So and VHF, UHF, SWR motors are much more expensive than HF ones because there are lots of different things you have to consider for the higher frequencies than you do for HF. But you can get meters that measure both. Yes.
Thank you.
Okay. I'm not going to go into a lot of detail on this, but I'm just going to say that the blue wave is the forward, the red wave is reflected, and when you see the green wave, that's the algebraic sum of the interaction between those two waves in the transmission line. Then what's happening here? Okay. So when you look at the effective SWR on output levels, the table doesn't consider, by the way, the transmission line losses. So output power is also related to the emission type and bandwidth. For example, a 2.8 kilohertz SSB signal will have a lower average power than a maximum output setting. So if you set your transmitter for 100 watts and you look at the average power for an SSB signal when you're talking into your radio, it won't necessarily be 100 watts. It'll be lower because all the energy of your voice is that 100 watts is being distributed across all the energy from that voice in that modulated signal. So it's not going to necessarily be at 100 watts at all times. Versus FM, which is when you talk at FM, you're at full power. Or at digital modes, if you set it for 100% power, you're going to be at 100% power in digital modes. Typically, we aim for 1.5 to 1 ratio or less across a band. That's when if we're adjusting or building an antenna, that's what we go for. And most radios can handle about 3 to 1 before they begin to self-protect themselves. But let's look at the facts. If you didn't consider line losses of a transmitter, then how much did you lose at 1.5? You lost 4% of your power. Can you live with that? Probably. Look at 3 to 1, you lost 25% of your power. Well, that could be a big deal when you're operating 5 watts, and it could be a moderate deal in 20 watts, but it's not a big deal at 100 watts. So you can live with these losses if you needed to, and it may not have much effect that you can look at. However, there are other situations that this contributes to that you have to be thinking about. So what we normally look at is when we're tuning an antenna, as long as from one end of the band to the other end of the band that we're using the antenna, we're at 1.5 or less across that space, we consider that a good bandwidth. And so that's just to keep an idea that what's happening to power. Now, what happens to reflected power? This is interesting. Is the energy bounces back and forth inside the cable until it's all rated by the antenna for a lossless transmission line. And I'll talk about what that is in a minute. I gotta just realize I'm only halfway through my slides. I better speed up. So when the energy comes up, and remember that energy is bouncing back, the SWR, the standing wave is bouncing back. What's happening? Well, if the energy is a lossless line, it's going to hit the transmitter. And if anything's not absorbed in the ideal sense from the transmitter, it's going to go back up the line and back down the line and back up the line and back up the down, back and forth until, but as it's going back and forth, guess what's happening? It's radiating. It's actually still radiating because it's energy. So in the ideal situation, energy bouncing back will radiate back and forth the antenna and lossless line. but coax isn't a lossless line. Okay. And not all transmitters can handle that bouncing back and forth. So most transmitters, most transceivers protect themselves from high SWR because solid state equipment doesn't like high SWRs. It can't handle that much reflected power. So to protect itself, a modern transmitter will throttle back its output to as low as it can go to keep the SWR from damaging it. So just so you keep that in mind, it folds back over. But coax is a lossless cable, which means as the energy goes up the line, there's some losses. And if the energy is reflected back, there's losses. And if the energy is reflected back up, there's losses again. And comes back, there's losses again. So there's losses. And that losses is dependent on the frequency. So different cables have different loss factors. So for example, if you use RG8X at the bottom, and in HF at 30 megahertz, you can lose, for every 100 feet, you'll lose 2 dB. Almost, let's say, a little bit less than half power will be lost in the coax in one direction if it's 100 feet. Versus LMR 400, for 100 feet, you've only lost 0.7 dB, which is minuscule. And therefore, you're putting more power. You're having less loss there. You have more power to the antenna. So, and again, it also depends on the run. If I only had a 10-foot run, would I use RG8X versus LMR 400? Yeah, I'd use RG8X for a short run. Why? It's cheap. It's relatively cheap. LM 400 is expensive, relatively speaking. So if I have a short run, I don't care about the losses. I care about the expense. Now, at my house, when I had my antenna up, I had about a 100-foot run almost. So guess what I bought? LMR 400. Why did I buy LMR 400? Because I used LMR 400 for my VHF and UHF antenna as well, because you can see how much loss you have when you get up to 50 megahertz, 150 megahertz, and 450 megahertz on these cables. So you want to size your coax to the amount of loss that you're willing to take, given the expense. Okay? So just keep in mind, antennas, coax line has a loss associated with it. Some fittings have losses associated with them, and some switches can have losses associated with them. Good fittings and good fittings have good switches have very little loss, but coax is a source of loss, and you want to think about the length of the run versus the frequency and how much loss you're willing to take from that coax. And so how do we fix it? So we have this 200 ohm impedance here. We have 50 ohm. How do we fix that to get a match? Well, we have to somehow get the 50 ohms from the transmitter to be looking like 200 ohms to get a maximum energy transfer. And we need to add an impedance transformer. And this is an impedance transformer. People, you may have heard of this as a Balam or Un-Un. And that's an impedance transformer. In this case, it's trying to change the impedance from 50 to 100 ohms. And notice it's up at the antenna. It's up at the feed point. Why? Because there's 50 ohms, the transmitter sees 50 ohms. The coax, because of 50 ohms, sees 50 ohms. And that impedance transfer, the antenna now sees 200 ohms. And so there's a maximum power transfer through the impedance transformer. So that's what the impedance transformer is doing, is it's making sure, as an impedance transformer, that we're matching the antenna to the transmission line. And that's how we make sure we have maximum power transfer, more or less. So, but was this, when we look back at the 50 ohm, 50 ohm, 50 ohm match, the question we have to ask right now is, was this really a match? And the answer is no, it wasn't a match. Why? Because there was another source of reflected power. And the other source of reflected power is the coax. Because coax is spooky stuff. It's actually doesn't look like 2 wires to RF. It looks like 3 wires to RF. 2 wires are going to the antenna, the braid and the center conductor, but one side of the braid is also another conductor because of the skin effect. And so that other conductor is where the reflected power can come in. So what can happen is that when you have coax, which is 3 wires, attached to an antenna dipole, which is 2 wires, you have an unbalanced antenna system. You're trying to connect a balanced antenna, 2 equal legs, to an unbalanced coax, which is like 3 wires from an RF point of view. So we need some way to force the current to stay on the antenna, when we do this kind of match to match the transmission line, the coax to the antenna, and we do that with a balanced line to an unbalanced transformer called a balun. And the only job of a balun is to force the current to stay equal on both legs of the antenna when you're matching against the coax. It doesn't do impedance transformation. All balums are 1-to-1, period. Well, David, I can buy a 4-to-1 balun. Absolutely. I can buy a 6-to-1 balun. Absolutely. Well, how is that possible when you say it's all 1-to-1? Because every 4-to-1 and 6-to-1 and 2-to-1 balun has an extra toroid impedance transformer attached to it. There are actually two. One's acting as the balun to cut off the common mode current, and one's acting as the impedance transformer. If you have an unbalanced line, like an end-fed antenna is an unbalanced antenna, because essentially there's only one leg. There's actually two, but they're unbalanced. And because you need to do an impedance transformation for an end-fed antenna, which is about 2,500 ohms, and you only have 50 ohms coming out of the transmitter, you need an unbalanced impedance transformer, otherwise called an un-un. And so I like to use the saying that every antenna wants to be a dipole. An end-fed antenna has to have the other half of its antenna. It'll either make the coax shield the counterpoise, or you'll have to add a separate short counterpoise. But every end-fed antenna or random wire antenna needs a counterpoise. It will find a way to find and make one. And so what you do is you can use the shield of the coax as a counterpoise or a separate counterpoise, but you have to have an RF choke to remove the common mode current before it gets to the transmitter. And that's why every end-fed antenna not only has a 4-to-9-to-1 or 64-to-1 impedance un-un, transforming un-un, it also has later down the line an RF choke to protect the transmitter, just so you know. Getting tired. Okay, so now if we put a 1-to-1 balun at that antenna, now we're matched, because the 1-to-1 balun doesn't do any impedance matching, but it helps force the current to be equal on both sides and chokes off common mode current entering the transmission line. And as I said, a 4-to-1 balun actually has an impedance transformer attached to the 1-to-1, and the same goes with, and then there, of course, are the un-uns I mentioned a second ago, which are just impedance transformations. And of course, lossless cable, some of you are familiar with it or heard about it, and that's ladder line or window line. These cables are called lossless because they are truly just two wires, and the currents flowing down one side are actually canceled out by the currents flowing on the other side. So that's why these are lossless. If you want to have the least amount of loss in your transmission line, these are the way to go. However, you still have to do an impedance transformation to match the impedance at the antenna feed point. That you still have to do. And we talked about this. This is just going back to, if we fix the 4-to-1 matches, we've matched the 200 ohms for the offset fed dipole. What happens when it's not 200 ohms? That is, when you go off frequency, off the resonant frequency, the impedance is going to change. How do we compensate for that? We don't. We just basically say it's good enough. Or we use an antenna tuner. So what we do is we put an antenna tuner in the line. And by the way, an antenna tuner, I like the old term for antenna tuner better. It's transmatch. A transmatch is basically a inductor capacitor circuit that does the impedance matching for you. It can be manual or automatic. And what that does is allows you, as you change bands or frequencies, to further compensate for the impedance mismatch between the antenna and the transmitter. However, you notice it doesn't fix the antenna. It doesn't do anything to the antenna at all. It doesn't tune an antenna. In fact, all an antenna tuner does at that location is make the transmitter see 50 ohms. That's what that does there at that location. It doesn't match differences at the antenna because it's not in the right place. So, but it makes the transmitter see 50 ohms. So therefore the transmitter is happy, and it will try to get maximum power up into the transmission cable. But if you move the antenna tuner to the feed point, then you're doing a better job at matching the impedance differences between the radio and the antenna itself. And then you'll have better maximum transfer there. I'm going to stop here and see if there's any quick questions. Okay. All right. We're going to go through this part fairly quickly. So great radio, and I've talked about this. Great radios with marginal antennas are often not as good as average radios with great antennas. So it's sort of like stereos with good speakers versus stereos with bad speakers. That's what it comes down to. So transceivers, popular, these are the popular rigs. You can see that they run the gamut. Some of these are 20 watts. Some of these are even 10 watts. There are 5-watt ones. But otherwise they don't go above 100 watts. Some of these, like the FXCR2, I believe, and maybe the ICOM or the SBICs, they actually have digital mode built into them. So you can actually operate some of the digital modes inside those radios without having a computer. So some of these rigs, like the FT991A, which is what I own, is a shack in a box because it does VHF, UHF, and HF. And so that's what I prefer, is to have that one radio. Now, if you looked at these prices and went, oh my, and they get a lot more expensive than this. I think there's $13,000 one there. So are you getting any sticker shock when you look at this? And the answer is, don't worry, it's a normal reaction. Everyone gets sticker shock. Used equipment is a good way to get started. That's how many of us got started with used equipment. Also, if you want to look at a $1,300 radio divided by 15 years of use is only $87 per year or 24 cents a day. Isn't that great? What a value. And radios generally have a good resale value, which is a great explanation when you're talking to your spouse. So keep that in mind. Used transceivers generally are $200 and over. And here's just a sampling of some of them. I used to own a 440S. I love that radio. I just wanted to get something more than that, but it's great sound for a Kenwood. It's a Kenwood. I like that radio. But will you do just as well with an old radio as you can with a new radio? Sure. You get more features and more functions with a new radio, but will it still function an old radio? Absolutely. If it's well maintained and still puts out power, it's a good radio. Again, put a good antenna on it. You're all set. I also own the FT897 here on the left corner. I bought that used for $800 and I sold it used for $1,000 with all the accessories. And I now have the FT991A, which has replaced that one. And then models do evolve. So here's the 1971 FT101. And in 1985, when they discontinued the 85, it was a ZD, 101 ZD, and it had digital readouts. So these are older radios, and they do evolve. And you can see, though, that at some point in time, there's a lot of buttons on these radios. And they do lots of things. But there's still a lot of buttons on the radios. And that's great because it looks great. It's cool to have a lot of buttons. But modern radios, there's a big jump in the 2000s with modern radios because they have, you notice there's less buttons. But these radios are computer controlled to one extent or another. And they have many more features. I mean, literally 100 pages of features that you go through different menu structures to get to. You can see the FT897 has LCD screen. It's got a whole bunch of, we'll go into some menu features. But here's the replacement, the FT991 in 2014. And you can see it's got it has got a waterfall display. It's got soft switches and complex menu structures for doing anything you can think about. Let's mute the lines, please. Okay. And then we have the newest radios are software-defined radios, which are not necessarily new. They've been out, but in the amateur radio market, they're 20 years or younger. So we have to remember that electronics is all physics. It's very, very much physics driven. And the language of physics is mathematics. And all radio functions, therefore, can be expressed as a set of mathematical functions. Analog hardware is discrete fixed hardwired expressions of these functions. So when you build an analog circuit, it is a hardwire expression of those mathematical functions. SDR radios are primarily a library of mathematical software functions orchestrated by a program with some supporting hardware, like analog to digital converters, digital analog converters, and amplifiers. So because they're all done in software, you now can do things mathematically in the radio that you used to have to do physically with hardware. So let's say we have a 2.8 kilohertz SSB signal. With a few button pushes and some knob turning via software, I can change the bandwidth of the high pass filter or the low pass filter. I can change the characteristics of that in receiving wave or output wave. And so what does that mean? Well, now that's really quick and easy. I can do things with that versus in the old days, I could have put a filter into my radio, in this case, a 2 kilohertz filter. It cost me about $90, but that's all I can do is a 2 kilohertz filter. If I want a 2.4 kilohertz filter, I have to buy another module. If I wanted to have a 1.8 kilohertz filter, I had to buy another module. And here I push a few buttons and I dial in what kind of filtering I want for the different band conditions. So that's the power of one of the powers of an SDR radio. And SDR radios usually typically have feature-rich interfaces. This is a SDR Sharp. Unfortunately, the screenshot's not that great. But it's a waterfall. You get to see what's depending on the size of your sound card, you can see as much of the band or as a sound card will let you, and you can literally see all the signals there, and there's all sorts of filtering and things that you can do in software through the computer. So in this case, you can attach a modern radio can often be interfaced to these programs, and you'll have control over things that in the radio you didn't have control over because you can do it in software. Or SDR radios like the Flex, this is all basically all done this way in the Flex. So just coming to the station, when you consider the station, you have to consider the station cost, not just the transceiver. So for example, does it have a built-in tuner? If it does, will the built-in tuner be sufficient given your antenna? Is your antenna, if your antenna is 10-to-1 SWR and your built-in tuner is only good for 3-to-1, then it's not going to work. You're going to need an external tuner. So, but most people who build their own antennas and it's a fixed location, it's going to be less than 3-to-1. So a built-in tuner on a transceiver means one less box to have to buy. Do you want to interface it to a computer? Yes, that does have a modern USB or an old RS-232 port. If it's an old RS-232 port, then you're going to need an adapter to interface it to a new USB-based computer. If you're going to operate digital, do you have a built-in sound card in the radio? Like the FT991A has a built-in sound card. So if not, you're going to need an external interface to do digital. Does it have a built-in 120 volt AC to 13.6 volt DC power supply? Some very rare that they do. The FT9897D mine did, but FT991A does not. If not, then you'll need to purchase a power supply to operate from home versus batteries. And if you operate portable at home do you operate portable or you want to operate during a power failure, you're going to need batteries or a generator that are sized to the need of your power and typical use in RF power output. And if you're traveling with the radio, then you need to consider a hard case or a padded pack to take the radio. So these are all the things you want to consider when you're buying your radio, all the different questions that will change the cost of your station, the ultimate cost of your station, including the antenna. So let's focus really quickly on some of the basics of operating, because if you can operate a modern radio, or even some of the older radios, you can operate pretty much all of them very quickly. You get to figure them out. So this is a release in 2002, discontinued in 2014. This is my radio before the one I have right now. So modern rigs have lots of features and deep menus. It can drive you crazy at first, all the menus. You can see on the left in the yellow, there's buttons that go underneath the panel, underneath the LCD screen. And I have choices from those buttons based on the LCD setup. So I can use the multifunction button, which is the one on the right in yellow, is a dedicated button where I can use that to go through the menu structure that sets up different SAW switches. And then I can change the values of the things in the SAW switches by rotating the tuning knob when I'm in that mode to change the settings. And that's how you go through the menus. You put it into into feature mode. You adjust the dial to get to the feature you want to deal with. You then select the section that you want to deal the soft key to which section you want to do, and then you rotate the knob to get to the setting you want, and then you exit the menu mode or the feature mode to take care of that, to set it into memory. There's also software you can plug your computer into your computer, plug your computer into the ports of a modern radio, and you can do a lot of this without going through the menu structure, but through your computer with a dedicated user interface. But here you go. Here's the FT89, the replacement radio, and you can see there's my different menu setups on the red, and there's my multifunction dial. So I went right from the old radio to the new radio, and I could find very quickly the same kind of setup. Oh, and here's the ICOM 7300. Look, a multifunction knob, menu structures, how to get into them. Look, it's the same basic functions. They're being titled sometimes differently. They may be laid out differently, but they're there. Let's say but you have, in this case, 2 VFOs. Almost every radio, HF radio, has 2 VFOs. Anything that's, within the last 25 years, it's got 2 VFOs. And each VFO operates independently of the other one. They're basically two separate receivers. And why 2? When stations are operating split for pileups, they'll different license classes and different country rules, they'll operate split. So let's say I'm a country, I'm outside the United States, I'm in a small country that everybody wants to talk to. So the minute I say, EX12 BB, I'm going to have thousands of people calling me, and it's going to get crazy. So what I can do is CQ call sign, CQ call sign, up 5, CQ call sign. What does that mean? It means I'm going to transmit where you're hearing me, but I'm actually going to listen for you 5 megahertz higher. And that way I'm keeping all the people who are screaming at me in one place, while the person I'm talking to is going to hear me clear because it's just he and I, okay? And so that's called split. And so what I would do is set up my radio so that I would have 1 VFO for receive, 1 VFO for transmit. I push the split button, and now I can be, when I'm listening on one frequency, and the minute I hit the push to talk button, it flips over to the other frequency for transmit. Hey, that sounds like a repeater. Yep, that's exactly similar to a repeater. Oh, by the way, that's exactly similar to satellite communications, where you have an uplink and a downlink. So guess what? When you're doing uplink and downlink with a radio for a satellite, you're operating split. So that's what split does. And here we have, look, here's the newer radio, AB, and split. It's right there on the dial too. And here's the 7300, split and AB, right there on the dial. It's the same commands. And so, of course, now with modern radios, you don't have any gears and strings doing the tuning. It's all done with an optical encoder. And a tuning knob and a menu setting determines the step changes as you turn the knob. In some rigs, the faster you turn the knob, the faster the frequencies move. In other radios, it will always be the same rate. And then some have this really strange one. This is the G90. And the way they do it, they still have an optical encoder for tuning, but you push the button to adjust which of the digits you're going to start the tuning from. So if you want to do coarse tuning, you push the button until you get to like the 2 or the 0, and you start tuning from there. And if you want fine tuning, you go to the far right digit and you start tuning, push the button and start tuning from there. I hate that, but I'm learning to live with it. And here, if we want to stay on, if we're staying on frequency to do a lot of communications on one frequency, and I don't want to accidentally bump the tuning knob, I can lock the tuning knob. And so there's a lock button. And by the way, on this unit, there's a blue button where the power button is. If I push the blue button, it'll set the tuning knob into fast mode, which means I can move, as I move the knob, the rate of change of frequency goes up fast. So that, in other words, if I'm tuning like this, it's normal. And then I push the fast button and I'm tuning just at the same rate, it's going to go up at a higher rate in tuning. And then I can untune that. And by the way, here is the same thing on 2 other radios. TS and the 5.6 Pro is the fast and slow speed. So again, same kind of controls. Band mode switches, up and down and left and right, changing modes, CW, SSB, or changing bands. By the way, this is the same control in the G90, it has similar control. In the 5.6, so most radios have similar controls on the top on the front panel. There's a clarifier control, very rarely used, but let's assume you're at 21.295 and you're calling CQ, a station answers you, and they sound a bit off frequency. And there could be a lot of reasons why they're off frequency. They could have bumped their knob without realizing it. They may have an old radio where the VFO drifts a little bit, or the person, because their hearing is a little bit different, they're not on frequency with you because it sounds right to them. So you can activate what's called the clarifier or the receiver incremental tuning, and you can adjust that button so you can hear them better, but it keeps you on the same frequency. It's just shifting that for that one time, and then you unclick the button and it'll go back to normal. There's also a transmitter incremental tuning as well for the same reason. And these controls exist here on the 5.6 Pro as well. And they can exist on other means as well. So automatic gain control is common. You can set the average, fast, or slow. There's different advantages for AGC. Fast is good for when you're working, times when you're working strong stations and there are weak stations next to it, or vice versa. And that way the automatic gain control will very quickly readjust to changes in the signal strength. Versus slow is good when you have both stations are strong. It eliminates excursions in the gain when someone stops talking for a moment. And then average, of course, makes sense. It's just in between. And then we have the volume control, which is AF, and we have RF gain. Very helpful for cutting down the RF amplifier gain to reduce noise. It alters the base of the AGC in response. So you adjust that and you'll see your AGC meter change as well. Don't assume the best setting is the highest RF gain, because when you increase the RF gain, you increase the noise as well, and then you may be increasing the distortion that you're hearing in your ears. Too much noise, and it's hard for you to make out what the person's saying. So oftentimes you turn the gain down and you interact between the AF and the RF gain to find a place where you've minimized the noise enough that you can hear the person over as best you can. And then there's a tune button. A lot of radios have a tune button. What's it for? For those antenna tuners that are automatic and can interface with your radio so that it will control your radio while it's tuning. So if you press the tune button in the upper left corner, it's attached to my radio on the right. It will automatically turn the radio transmitter on, set it for low power, and automatically start the tuning process until it's done, and then turn the radio off. So a tune button will automatically tune the radio will activate the tuner inside tuner. If it's built into the radio, it'll activate the tuner. If it's outside the radio, it has a setting in your menu to cause the external tuner to be functioning if it's an automatic tuner. And this is an external tuner on top of my radio because I use a lot of different antennas. I might have to go beyond 3-to-1 SWR. And so I have a external tuner that when that happens, I can put on that will then allow me to work with more variable antenna systems. And the tune button is what automatically synchronizes with that MFJ box. And so the radio is controlling that tuner for me. And of course, there's still manual tuners. They're good. They're fine. And there's the remote tuner for base antennas, which go right to the base of the antenna. They're more expensive. They have to be waterproof. And they are controlled by the RF coming down the line. And they automatically will make the antenna and the transmitter matched at the antenna. I won't go into this because you can get this, but there's a lot of different other common controls. You can see preamp, attenuator, RF power adjustment, noise blanketer, digital signal processing, compression. There's a lot of CW controls. If you do CW, there's lots of CW controls. There's voice operator relays. There's switching between VFO and menu mode. And of course, all the storage and retrieval and labeling stuff about memory. What we just went through is, if you know these controls, you can operate pretty much any radio out of the box. And then if you want to get deep into the menus to make real adjustments, you of course have to read the manual. But if you know these controls, you can pretty much very quickly learn how to run any radio that's out there. Operating stuff, let me check the time. Oops, guys, I am probably behind by 20 minutes. Is that all right to stay on? I'm going to keep going, and then if you want to hang up, you can hang up. We don't have too much left to go. And so I apologize for going over, but I'm going to do the best I can. So one thing when you're operating a radio, and you may have experienced this, is some people experience like stage fright, mic fright. It's natural, it happens. The only way to get over it is to basically do it. And maybe having somebody who's an operator, who's experienced operator, come with you and start operating alongside you is helpful for getting over a mic fright. But also with HF, you want to listen first. Find out how their cadence, find out how they're talking, or how their CWs, whatever the mode is, you want to listen as much as you can before you start transmitting when you're calling to a specific station. Listen for anything like split up or down by some number. It indicates they're splitting. Station call CQ, answer with your call sign and wait for response. Again, when they say again, it means to call out to your call sign again. So they might say CQ, CQ, and you come back Whiskey 7 or W7DAO, and they might come back and say again. You don't know who they're talking to, but you just assume it's you, and you say W7DAO. They might say W7DAO back to you, which means you can go and talk to them. Or they might say, Whiskey 7 station, who is it? Or what is it? Whiskey 7, come back. And you can say, okay, assume it's you. Whiskey 7 Delta Alpha Oscar. Okay, Whiskey 7 Delta Alpha Oscar, go ahead. Or they might come back and say, Whiskey Delta Station, please. So until they can sort out your call sign, they'll keep calling what they know until they can get it right. And if they say they finish with somebody, when they finish with somebody and say QRZ, that means they're ready for the next call. So if they don't, it's not like saying they don't have to say I'm waiting for the next call. They can say W7DAO QRZ. That means they're ready for the next station to call them. If they wait a long time, if you're listening to them and after about 20, 30 seconds, they don't have a station, they'll start calling CQ again. So QSL means did you copy or I copied? So I might say to that person, they might say, W7 station, come back again. I might say, Whiskey 7 Delta Alpha Oscar QSL, and they'll come back Delta Alpha Oscar QSL, which means I'm asking, did you copy? And they came back and said, QSL, I copied. Two stations talking and you want to break in. When there is a pause, state your call sign and wait. You might have to wait for another pause and try again. So, and after a couple of times, just move on. If you've got emergency traffic, I'm a firm believer when you're in voice communication, state it. Be obvious. This is W7DO. I have emergency traffic. You could say, like in VHF, UHF, break, which is emergency traffic, but I'm a firm believer in saying being explicit. And yes, you can say over. W7DO, or you can say, hey, I'm having a great day. Weather's great. Works fine. Over. That's okay. Totally all fine to say that. This is what we just went over about some CQ stuff. I went over that a little bit already as I was going through the exercises. If you're doing a contest, the exchanges are very, very fast. Contacts are about 15 seconds at the most in a voice exchange. But you need to read the contest rules and understand your part of the exchange before you get on the air. And get that prepared. You need to know what you're going to say before you get on the air for the contest exchange. Find the clear frequency and sit and call. CQ contest, CQ contest, CQ contest, W7DAO, Whiskey 7 Delta Alpha Oscar, CQ contest, CQ contest. This is W7DAO, Whiskey 7 Delta Alpha Oscar. Listening. Wait for someone to call. If they don't call, start CQ again. CQ contest, CQ contest. That's what I like about my modern radios. They have a voice recorder built in. I record that. I just push the button. I don't have to say it. Hunt and pounce. That's what I normally do myself, is I'm scanning from one end of the band to the other. And when I find somebody who's calling out CQ contest or whatever it is, then I will try to get that station. When I get that station, I will then move on, start scanning again. I don't sit on one frequency. It's called hunt and pounce. Always listen before calling a station and I find it helpful to write down on scratch paper their call at an exchange. Because sometimes if you call them and you keep saying to them, what was it? What was it? What was it? That's irritating to everybody else listening. When all you had to do is listen for about 2 minutes or less and write it down and have it ready ahead of time so you didn't have to ask them to repeat. Then try to make the contact. The bands are very busy and crowded. This is a good time to use your RX gain and your filters to reduce your receive bandwidth so you can reduce some of the interference from the hundreds of stations all calling out next to you. So a sample of logging software, I won't go into that, but there's lots of, if you put in, there's a lot of software out there for logging. Aerial has Logbook of the World. QRZ has their own logs. Ham Radio Deluxe is software for controlling your rigs and doing digital. It has a log. Contest logger that's very popular is N1MM. It's a very popular contest logger. If you want to compete for points and awards, you need to log your contacts. And most contests want Cabrera format. So you want to make sure that your logging program does that format, or you have a converter for doing that format. So you can send the logs in. This is my QRZ. This is a sample of one of my log sheets from QRZ. This is from a station I talked to in Japan just recently. Excuse me. And then powering it all up. Let's just finish up with powering all up. Typically, radios prefer 13.8 volts DC. Amateur radios are designed to operate in the 12 to 13.8 volts, with some accepting voltages as high as 15 or 16 volts DC. But with max output at 13.6. Why 13.6? It's what a car battery generally has been historically. That's why it's 13.6. Because a lot of these radios were built to be in cars, no matter how many thousands of pounds they are. So, but modern radios generally have a low battery cutoff because they're digital. And so they have 10.5 to 12 volts DC is what they consider a good operating value for them. Below the cutoff voltage, they have trouble operating their circuitry. So they cut off if they get to that point. To attain maximum power output from the radio, you need a source of sufficient voltage and sufficient current. If you do not have sufficient voltage or current, you're not going to get the maximum power from the radio. And so you want to size the power source with a slightly higher current rating than you need. So power requirements, they vary. 20 watts maximum output on G90, it requires only 8 amps to operate. 100 watts max output on my radio, my other radio, is about 22 amps at 13.6 volts. By the way, if I drop and operate 20 watts on my FT991A on the right, of course it's going to be closer to 8 amps. So power output determines how much current you're going to use. So if I drop it down to lower powers, I'm going to use less and less current on the right side versus the left, which is a QRP radio. So, and of course, all wire has some resistant losses to it. So you have to choose your wire to handle the amount of current you're putting out. So for example, on the right, you see different amps capabilities of different wires. You can see that for most amateur equipment that uses 100 watts, we'd like to have at least 30 amp or 10 gauge wire. If the run is really, really long, we might go to 8 gauge wire to reduce the voltage losses. So remember, the longer the run on smaller gauge wire, the higher the DC losses. And you want to size the wire gauge to the current needs of with some safety factor, because all wires are fuses. And if they get too much current that's beyond their rating, they will melt and the insulation might catch fire and they'll break the circuit. So remember, every wire is a fuse if you exceed it. Power sources, there are two basic power sources for line power. One is linear. It's where you plug into the 120 volts, has a bridge and a transformer, regulation, and it gives you, it's much heavier because the transformer is so big, has less RF noise, and they're more expensive. Switching power supplies, which use an oscillator to use a high frequency transformer, which is much smaller than a 120 volt 60 hertz AC transformer. They're lighter, but because they use a high frequency transformer, they generate more noise, but they're less expensive and less and more affordable. Batteries, sealed lead acid, they're heavy, 300, 500 cycles, less expensive, and they have a cutoff voltage. Most people are moving over to lithium iron phosphate batteries. They're lighter. They can handle 3,000 cycles or more. They're much more expensive. They do have a cutoff voltage and they have an internal battery management system, but they are much more durable and lighter than sealed lead acids. Generators, of course, are available if you want to use them for operating and charging. And a lot of people, and myself included, use solar power, either for, if you can handle it, enough solar collectors, you can operate your QRP radio that way, or at least, like I do, it's for charging my battery when it's not in use. There are other power supplies that are much cheaper. For example, a computer power supply for computer racks is generally about $30. They can handle a huge, 60 watts, 60 amps, but they're switching power supplies with very little isolation for noise, and so they have lots of birdies or noise harmonics that go on your radio. A switching power supply for amateur radio is much more expensive, and the reason they have noise offset control, so they can reduce the noise that's being induced into the transfer from the power line. So that's the difference. By the way, I use the $29 one. I live with the birdies. Battery boosters for when you're on your battery. This is a device that boosts the DC voltage coming in from the battery to a higher level going out. So if you have a 12-volt battery, it'll give you 13.8 volts output. And then these are sized for the number of amps that you need. And that helps keep your battery operating at maximum efficiency for a longer period of time. Solar charging, you need a solar controller and charging panel, and it's good to have a home battery charger for your battery as well, because it takes a long time to charge a 30 amp hour battery. Now I use a 30 amp hour battery when I want to use 100 watts when I'm operating portable. Power failover switches, you can use those so that you have a battery going in and a power supply. And if you want to operate with automatic changeover, that you don't have to do any rewiring, you can have your battery and your power supply into your radio. And if the power fails, it automatically cuts over to the battery for you. Why are there 2 fuses on a power line for amateur radio equipment? It's if the grounding point should lose its integrity, excessive current could flow through the transceiver's negative lead. It also prevents a minor ground loop between the leads, and that's why there are always 2 on an amateur radio equipment. There are always 2 fuses, 1 on each side. This is a setup for 100-watt operation that I use. I have fuses, I have battery capacity meter, my booster, and my radio, and that's my typical setup out of my battery boxes, which are right here. Here's my battery boxes. Carry my batteries with me. One's charging and one is in use at all times. This is my G90 Go box. It has the G90 radio, a battery, and the booster all in one setup. And then I just set up and go. Digital. I am going to stop here. I think I am over time, but also getting tired. So unless I think I have about 10 more minutes, so I went digital, but I'm getting a little bit tired. I'll just stop here and ask if anyone has any questions. By the way, the SDR Play is nice radio, nice setup. Anyone have any questions? By the way, first, thank you for staying with me all this time. I give you the, congratulations.
Question?
Yes, go ahead.
Did you say that this is going to be on the Mike and Key YouTube page?
Yes.
Oh, great. Thanks so much for everything. You're doing a great job.
My pleasure. Any other
I don't
questions?
expect.
Oh, go ahead,
continue.
Bob. Go ahead, Bob.
Thanks so much.
Okay. Any other questions?
Yes, I have a quick question about SWR.
Mm-hmm.
If I put a kind of like a what do you call it with electricity? I'm kind of drawing a blank here. But when a surge comes through, if you put a device to stop that surge, will it stop the SWR?
Okay, so I didn't talk about lightning arresters or surge protectors for lightning. They should be on every antenna you've got, and its job is to, if the lightning comes, it's supposed to shunt that to a ground rod, and that hopefully will protect your radio. There's also the other side of that is if you plugged into a power supply, plugged into house power, do you put a surge protector on the house power entering into the power supply to protect the power supply? Yes, if the power supply doesn't have its own surge protector, it's probably worthwhile to have a surge protector on your line to protect your power supply, $190 investment. On the lightning side, I'm a belt and suspenders person. I would put a lightning arrestor on, and I'd have a coax. I would have an antenna switch that I could switch to ground when I'm not operating the radio, so that when I'm not there, if even the lightning arrestor doesn't give a complete protection, then the radio is disconnected from the antenna. Does that answer your question?
But does surge protection help against SWR?
No.
Okay. Because being where I'm from South Carolina and coming here, like there's like zero lightning. So
Yeah.
I'm like not worried about that at all.
No, the surge protector will not activate until it gets sufficient voltage to fire. So it won't have any effect on the SWR normal operation.
Okay, roger that. Thank you very much.
No problem.
David,
Yes,
I got a.
that's a nice. Wait a second, I'm just gonna say, I think that's Ethan. That's a good comment Ethan wrote. So take a, anyone who's looking at chat, take a look at that. Go ahead with the other question.
Oh, I was going to ask you, can we follow up with you with some emails?
Yes, you can. In fact, there's my email. And by the way, I'll be at the Mike and Key swap meet at a table. So if you want, drop by, say hi.
Sure will. Sure will. Thank you. Doing great.
Any other questions?
Yes, I have a question.
Go ahead.
I understand that the Mike and Key swap meet is in Puyallup.
Puyallup, yes.
All right. So I'm from the East Coast, and the last time I heard about Puyallup was that it went totally rogue. So am I safe to go to this event, or do I need to enhance myself in some way?
Except for COVID, the Mike and Key swap meet has been going for about 40 years. It's not gone broke.
Okay. So I'm pretty much safe.
You are, I would say that if you're not safe, come to the table and tell me you weren't safe.
Okay. I'm just making sure because, I'm learning that things are a lot different on the West Coast than they are on the East Coast.
Well, the Mike and Key swap meet is probably the biggest swap meet in Washington State, possibly the Pacific Northwest.
Roger that, because I was hoping to go, but I didn't want to commit myself to anything that I'm going to get.
You'll be fine. Any other questions?
Yeah, David, I'm sorry. This is Ethan, Whiskey 7 Zulu Oscar. I just wanted to see if you saw that NFED half-wave common mode lightning arrestor question that I posted.
Yeah, would you say it again so everybody can see?
Sure. So I run an NFED half-wave, and I'm now trying to decide if I regret the way that I've been running it or not. I have it connected to my radio, and there's a lightning arrestor in between. During your presentation, you mentioned the importance of common mode choking for that NFED half-wave configuration to prevent current back into the radio. And I don't have it choked, but I do have it grounded. Is that sufficient? Because it's grounding the coax, of course.
Yeah, and the coax. Where is the ground rod actually located? As far as is it near the transmitter?
The ground rod. So the ground rod is about a meter away from the lightning arrestor on the ground, and then the coax runs about another 70 feet to the antenna.
Okay, so you are definitely, the ground rod itself is not going to bleed off that RF completely. And so the ideal situation is your coax. You don't have a counterpoise on the NFED, right?
I don't know. I'm just using the coax.
Okay, so the coax is your counterpoise. So I would say that I would recommend that you put a common mode choke in the line.
Okay.
I definitely would. And I would be interested if you could, in fact, here's something that'd be fun to do. If you, do you do digital modes?
Yes. In fact, I just finished my worked all states on FT8 with this configuration.
Perfect.
But I'm not sure.
Here's some fun. Here's some fun. And that is, before you put the common mode choke in, all within with the hour time frame, so to speak, with PSK or FT8, run that for 15-20 minutes on CQ.
Okay.
Then put the choke in, run for 15 minutes on CQ, then go to PSK reporter and see if there was any difference.
Yes, great idea. I will do that. I love an A/B test, and we're tabling at Mike and Key. I'll let you know what the results are.
All right, thank you very much. I appreciate that. Other question? And by the way, let's go back. What UNUN are you using? What ratio are you using on the UNUN on the NFED?
Oh, it's the ARRL kit, and it's a 49-to-1.
And they have the capacitors in there, right?
Yes.
Okay, good. And those capacitors are there to help with the higher frequencies to level it out, get it closer to the band. Okay,
Excellent. Okay.
good. Other questions? I can be here all night, but I won't.
Yes, this is Stephen again. I have one more question. Do you have a resource as far as the electronical equipment and a radio to kind of help me figure out what goes on inside? Because a lot of terms have been kind of thrown around that my dad would know because he's an electrician, but I am not. So I'm kind of wondering if you have a resource that will help me with understanding those terminologies.
So this is a good question, and the best thing to do is to send me an email stating it, and I'll send you
Comment?
some resources.
Comment?
Go ahead. Go ahead, Bob.
Amateur Radio Relay League, ARRL, has a bookstore on their website, and they have a series of books, basic radio, basic electronics, basic antennas, wonderful for filling in that lower level, beginning level stuff.
Yeah, that's
Very
a good
thorough.
That's a good source, and there's a number of good sources online as well that are for free. The other thing, I should tell you my background a little bit real quickly to make sense. I'm actually, my original training, not what I currently do in my real life, but in my original training, I'm a biomedical electronics technician. So I was trained as a biomed, and that was like a 3-year process, and learning how to fix medical instrumentation and scientific instrumentation. So that's my background, and did not get as much radio as I do now use, but I did get enough radio that I wasn't completely, starting from scratch when I learned ham radio. So, other questions?
I have some for you on the MFJ end fed. It has a ground strap, and I'm supposed to put it as close as possible to the ground and then run up and to the antenna. It's about 135 feet long. From where I put in the ground to the transceiver, does it make a difference on that run? Or I have to raise it?
If the ground, so I think if I correctly remember, the MFJ one that you're talking about has two terminals. One goes to the wire antenna, the end-fed antenna, and one is for a ground or counterpoise.
Strap, we got a ground strap it has
Right.
on.
And the ground strap is probably 17 feet long or something?
Well, they told me, I just got it, I don't know how to install it yet. They told me put it as close as possible to the ground within a few inches.
Yeah, that sounds like they're using it as a radial, and I'd have to go look it up because I don't know that one specifically. So if you send me an email and say, can you ask me the question and give me the reference, I'll look at it.
I'll either send you the picture and then try to understand, or I'll bring it with me down to this to the swap meal, one or the other.
Yeah, most likely if you read I suspect they have something in their documentation about whether that's running as a radial or is it running as a ground strap. Okay, thank you, Elizabeth.
Sure, but thank you, appreciate that. You bet. Thanks, David.
Okay.
Good night.
Good night. I think I'm done. I'm tired.
You sure?
So thank you all for hanging on there, and I really appreciate you participating in this. So thank you very much. Again, if you have any questions you want to ask me by email, there's my email address. And you may get an email from me if I teach I may be teaching an extra class in the fall. And if I do, I'll send you all an email.
Right. So that's that. So
okay. Have a good night, all.
Good night.
Good night.